All righty. Good morning, ladies and gents. Good to see you all this morning. And thank you once again for being on time. I really, really appreciate that. Now, I want to let you guys know this morning we are broadcasting live on our YouTube channel. So y'all be on your best behavior now. Yeah, we every now and then we decide to broadcast our classes live on the YouTube channel. Folks like to, drop in and see what it is we do. A lot of times when folks hear about, virtual classes, they think that they're going to get, some access to a YouTube channel and just be able to watch a whole bunch of, pre-recorded videos and stuff. So we try to give them a good idea that, that's not at all how we do our classes. Um, so every now and then we'll, with some of the other instructors, myself, we'll broadcast part of the class day on the YouTube channel. And anybody that's out there joining us on YouTube, welcome. I hope you guys get good bits of information about the class, about the way that we do things around here. I'm also going to, let's see where, there's the chat box right there. I'm going to go ahead and post my email address for the folks and you guys as well. Oh, I wanted to make sure now that class that you guys got the files downloaded from the wormhole site that I gave you guys the link to yesterday. That link will expire after a while. So you want to make certain that you grab all of those files before the expiration there. So, all right, got a full boat here going on. Now, first and foremost, do any of you have any questions about any of the homework that you were doing last night? I worked through all of the labs myself. There are both of the labs that we had. And I didn't have any problems at all. Now I've worked through the labs a couple of times before, but that very first lab that I gave you all was designed mainly to show you how to use the lab interface. And I've had students in the past that have, complained, and some just been concerned about the fact that there's not lots of instructions about the lab interface. So you basically have to, play around inside there and poke around, click here, click there, click everywhere, just get used to the interface. So, did anybody have any problems with any of those labs at all as we were going through or as you were going through your homework? How about it, guys?
I wouldn't say I had a problem. Like you say, you had to poke around with it a little bit to make it do what you want to make it do.
Oh
Because
yeah.
I think I plugged the power strip into itself one time.
Well, that'll blow you up now, there, Macklin. You don't. That'll light your hair up, man.
But
How
other
about
than
it,
that, yeah.
Kelly? Do you have any, Kelly? You have any issues with it? Kelly, I see your mic's hot, but I'm not hearing you. You may need to select the device again there. All right. Well, let's get on into this thing here. We've got 3 and probably 4 more lessons that we're going to get through today. The schedule pretty much the same as it was yesterday. We'll go through the first lesson. At the end of that particular lesson, we will be doing, of course, a lesson quiz, same thing as before. As always, if you guys have any questions whatsoever on anything that we're going through, you feel free to dive right in and ask those questions. I always welcome those. So, and we'll try our best to address them. Oh, I wanted to tell you guys something. I missed this yesterday. I've had students in the past emailed me or asked me real time. So how long have you been the expert? And I'm going, oh, wait a minute, back up. I don't claim to be an expert at this information. And technologies in general move so fast, so rapidly that nobody could truly be an expert on this stuff. And you'll find that most of the time, if somebody does claim to be an expert in just about any technology subject, you can bet your bottom dollar they're trying to sell you something. So, just take whatever they're saying with a grain of salt. Now, I will tell you, I've been in this arena forever. I told you guys I started when I was working on the computer's merit badge back in the late 1960s. So I've been around this block a whole bunch, and I have encountered, I would bet, just about every situation that you can think of from an A plus system support perspective. But I guarantee you, if I don't know something, I don't have a problem telling you I don't know. But then I always do my best to follow up and get other people involved if need be, because somebody in my orbit, other instructors, family, friends, and other assorted misfits, will be able to come up with an answer to just about any question you ask. Okay. So just bear that in mind. I'm not claiming to be an expert at this stuff, but take a look. I'm an old crusty dude. I've been around this block several times. So you're probably going to be hard pressed in asking a question that I can at least speak intelligent or semi intelligently about. But I guarantee you, like I say, if I don't know something, I don't have a problem admitting it at all, and I don't have a problem with asking others for help on it too. Now, one of the things that you're going to find that you will indeed be involved with as an A plus technician or a computer support technician is networking. Networking, hooking up networks, troubleshooting networks, working with different types, makes and models of networking hardware. And I'm talking about, including all hardware, your routers, your switches, gateway appliances, firewalls, server class machines, host machines, devices, your wires, all different types, 8-wire twisted pair, telephone cabling, coax cabling, fiber optic cabling. All of those things are utilized when we start putting together a network. Now, what actually is a network? If you take any two computer systems, doesn't matter what they are, one laptop and another laptop, a laptop and a server, a laptop and a piece of router or switch equipment, any two endpoints, we call those, that are physically wired or wirelessly communicating with one another, two or more, constitutes a network. Now we're seeing more and more nowadays in small, medium, and large enterprise environments. Networks are becoming more of a hybrid configuration kind of thing. Way back in the day, when the mainframe computer was the heavy lifting component, it had all the storage, it ran all the software, and then basically you had hardwired big dumb terminals, they call them, the CRT large screens, green screen kind of things that were hardwired to this centralized computer system. That was pretty much what was called the star topology, the way that those systems were actually wired up to that central control beast. You still see that in some situations now throughout networks, but we're also seeing other physical and logical topologies implemented, both wired and wireless. So quite the hybrid configuration on just about all enterprise networks now, even including the smaller networks like what we have in our homes. All networks begin at locally, and we call it a LAN, a local area network. Those are typically network systems that are in, typically anyway, the same geographic location. But once again, the modern versions of those things are wired and wireless configurations there. Okay. So, and again, doesn't really matter the size of the enterprise much anymore. Even here in my home network, I have a hybrid network configuration. I have total in the whole house, I've probably got a dozen or 15 or so individual appliances or endpoints that constitute my network. About half of them are communicating wirelessly to the wireless access point, which is my hub and my entry into the internet by way of my service provider. But also in that same device, the router, gateway, it plays several roles: the router, the switch, the gateway, even the firewall. I can configure it for that. But it has 6 physical communication ports on it. And I'm using up 4 of them that are hardwired to that box right now with your 8-wire twisted pair, people call it Ethernet cable. And then the rest of the devices, mobile phones, tablets, my wife's laptop, big, one of the smart TVs, they're communicating with that same box wirelessly. And then the security system, the mesh network, the Alexa that I use to talk to control some of the smart appliances, things like that. Those are, again, just a different configuration of a wireless network. Now, there's an organization known as the IEEE organization, the Institute of Electronics and Electrical Engineers. They actually are a large think tank, I guess is the best way to put it, but they also research and publish guidelines and specifications to the technical world in general about different wired and wireless configurations. And some of the guidelines that they publish also now have been adopted and dictate how specific pieces of hardware are manufactured and specific pieces of software are written for the manufacturers of networking equipment. They have in their wired world, they have the specification referred to as IEEE 802.3. So remember that for wired configurations, 802.3 is the specification that gives the guidelines, the framework, different ways that wired networks are configured, et cetera, implemented, and so on. And then for wireless networking, their IEEE specification is 802.11. Now, following the 802.3, there's different variances and versions of that. Same thing with 802.11. There's A, B, G, H, all up into AZ, AX, and so on. And it's just different layers and specifications that define the configuration of the hardware and the software that actually runs on it. So, like I say, it all begins with a local area network. Some of them are completely wired, some are completely wireless. Most of them are a hybrid mix of the two. But the LAN is usually in, like I say, in a singular geographic location. Now, when I begin to expand that outside of that singular geo, then you start getting into what's called a WAN, a wide area network. And there are multiple different versions of the wide area networking there. There's one called the Metropolitan Area Network, a MAN. There's one called a CAN, a Campus Area Network. Okay. There are wireless local area networks and wireless wide area networks. Now, one of the smallest networks we see, and folks don't even really think about it as a network, is with our mobile phone. Okay. Mobile phone and a set of earbuds. That's a network. That's a personal area network. I've also got a slick little pair of Bluetooth speakers that I hook up to the mobile phone. Well, that is a personal area network. Okay. I was telling you guys yesterday, here on my desktop setup that I have, I'm running a wireless mouse, and I run this curved keyboard that works real nicely with my carpal tunnel. But they both communicate wirelessly. So even that constitutes what's, a personal area, local area kind of network. Then we start branching outside of those particular network configurations, and we get into things such as these large storage data centers. They call them storage area networks. It's a complete standalone network. It has its own controllers, its own operating system, and it provides storage functionality for people that like cloud-based storage. People just want to store stuff off-site, archive storage, that kind of thing. Now, this is a really good example here of what's called a SOHO, a small office, home office network. You guys probably have this configuration in your homes. I do. I've got several systems here. Told you some of them are wired, some of them are wireless. They all communicate with this singular box here. This is sometimes referred to as the modem. It's called the router. It's the wireless access point. All of the above actually is what it is. It also provides what's referred to as the demarcation point. That's where the internet service provider. Am I back functional here now, Sloan?
Yeah, I
Yeah.
don't know if it was just for me. Did anybody else have employees that they want to go back a couple minutes?
Okay.
Maybe
Well,
it was just
well.
me.
Okay. All righty. Yeah. If anything you think needs repeating, we certainly will. Um, in this configuration here, like I was saying, this is called the demarcation point because it's where the internet service provider, whomever your service provider is, that's where their entry to the internet actually terminates into that particular piece of equipment. Now, in the not too distant past, that piece of equipment was actually broken up into 3 or 4 different pieces of equipment. It's the modem, which stands for modulator demodulator. It's the router box now, which makes the decision on if I'm doing internal networking or external networking. We'll talk about that later on as well. It's the switch where I can hardwire individual endpoints into it. It also is my wireless access point. Some of them have the antenna exposed. Most of them nowadays don't. Um, and then the access point coming into it from the internet service provider. Boy, that has changed especially over the last 2 decades. For the longest time, we had what was called ADSL or DSL modems. We'll talk about that more in detail later as well. DSL is digital subscriber lines, what it was. And that's when we were getting our internet service in on our regular landline telephone line. Okay. Well, that all changed, and we started getting these high-speed connections, specific network connections from the large providers, the telephone companies, AT&T, Verizon, Sprint, all of those. And they first started bringing it in the high-speed versions of it anyway, of course, using coax cabling. Now, many of them, even in remote areas, up at our little place in the Georgia foothills, we finally now have fiber optics up there. And the modem I have up there, the one I have here, the fiber optic comes through the wall and goes right into the back of the box itself, the router access point box itself. So very high speed coming in here. Now, a couple of those still in different neighborhoods are hybrid kinds of configurations. They call it fiber to the curb. So they'll have high speed fiber optic cable into like a curb unit of some sort or a unit in a cul-de-sac. And then from that unit running into everyone's homes, they're still running coax cabling. So the configuration and the wiring specifically is still varied. But it's all according to, how quickly they can get all the fiber optic cabling in the ground, so to speak, and wire it right into everyone's home. The SOHO part of it, small office, home office, that is a type of LAN, a local area network. Your single network appliance typically is this thing here. And again, it is the router, it's the gateway, it's the switch. It may also be the firewall. And I've even seen them that you can run antivirus, anti-malware software in that same box as well. So all of those functions are aggregated into the single appliance now. Now, some people tend to lease this from their service provider. Okay. I chose myself to purchase one that I wanted that was configured exactly the way I wanted it to or to be, and I have full control of all the configuration there on that. Still plugs in with my from the demarcation point out to my service provider, but I handle all of the configuration, all the functionality, everything in my own router gateway appliance. Now, this is a pretty good idea of going to an enterprise-wide type of network away from this scaled down SOHO type of environment here. Okay. Here's where we actually break down and sort of sub-segment or isolate and I do it departmentally or divisionally, what they call these work areas. The work areas typically provide some type of singular entry point for all of the devices. You know, here we have a patch panel that could very easily, in many cases nowadays, is a switch. These managed multi-layer switches, very intelligent switches. A lot of folks still use the patch panel in a wiring closet of some sort that, you know, consolidates all of these devices here. Okay. And then, but like say some of the work groups, they may have their own intelligent switch that all the appliances are plugged into, all of these guys here. Same thing over here, wireless devices, you know, mobile phones, laptops, tablets, phablets. Their primary communication is with the wireless access point, and then it is in essence hardwired by some means to some intelligent switching device. Then you will have these core, or they call it core switches or distribution switches, that all of these other switches and hubs and patch bays and so on that are piped into those guys. The switches typically down at the modular or the departmental level are, those things are very fast nowadays. They're somewhere between 10, 20, 30 gigabits per second. And then those are usually hardwired, oftentimes redundantly hardwired to multiple core distribution switches, which are then hardwired usually by multiple trunk lines to the outside broadcast equipment, the router gateway appliance that sits typically at the perimeter of the network. Okay. So these things, these core distribution switches, those are running real hot nowadays, 20, 30, 40, 50 gigabits per second, multi-line kind of things. So the hierarchical nature of that network, even with that, it's a hybrid kind of mix. You have the wireless, you have the wired by way of some type of wiring closet or patch panel. You have the wired directly to the high-speed intelligent switch. Okay. Sometimes you'll see that, and I've helped companies set this up before. They call it a DMZ or a screen subnet. Think about an environment that you want to set up in your particular network that is that only certain types of systems are isolated in that area. Only certain individuals or companies are allowed to get into that area of the network. They're not allowed to the rest of the network. And so that DMZ or that screen subnet, or sometimes called an extranet, by the way, it's usually sitting sandwiched between firewalls. Have an outward facing firewall and an inward facing firewall. And then the systems in the middle are usually designed to perform very specific functions. I set one up for a large company, or my company set one up for a large company downtown Atlanta. And in their DMZ, we isolated what are called jump servers. And we had 4 different jump servers in there. And they were only accessible by outside management entities. We had one that was managing the heating and cooling systems in the building. We had another that was managing all of the control systems that were in the parking garage next to the building. We had another company that managed all of the electronic functionality for the people moving things, the elevators, escalators, things like that. And then we had another company that controlled, they called it building automation systems, lighting controls. They had the smart windows that they could, you know, make them go opaque and clear and that kind of thing. But each of those management entities had their own jump servers inside that DMZ. So they would come into that from the outside world, and they would have to pass muster on that outward facing firewall. And once it validated who they were, they only had access to their system inside that DMZ. They didn't have any further access into the corporate network. But people that were just, employees, if they were dialing in, they were then routed around that DMZ, had to pass muster in that firewall to gain access to their systems internally. And it worked the same way on the outbound on that as well. So pretty tight control. We refer to it there as an extranet, but it's DMZ is the same terminology there. We also oftentimes put on the network perimeter, remote control type of systems, virtual private network servers, things like that, just put in there for additional security, that kind of thing. In the formalized data center in these large networks, that's where you have your high-speed servers. That may even be where you have your large storage appliances. The storage area network even may be there. Those things have to be tightly secured, of course. They also have to be, have a strict environmental fire suppression control, heating and cooling control, that kind of thing. But regardless of the setup, whether it's a local area network, a hybrid network, wireless, wired hybrid, whether it's the small office, home office, SOHO networks, or full bore enterprise networks, the concepts of moving data in and around that network are pretty much the same. You either have wired, hardwired connections or wireless connections. But in more situations than not, it is like this. It is the hybrid version. Hardwired directly to a switch, hardwired by way of a patch panel or a wiring closet, wireless to a wireless access point, then to the high-speed switches. And all of these things terminate at this demarcation point, we call it here. And that's where the service provider hands off their connection. Everything on the inside of that demarc is the responsibility of the company or the individual. Everything on the outside of that demarc is the responsibility of the ISP, the internet service provider. Now, there's several different types, excuse me, of specific networking hardware. When we think about networking hardware, we're talking about, or people typically tend to think about routers and switches. Well, it gets even closer to the computer than that and begins with the network interface card. We looked at a graphic yesterday of the NIC, the network adapter. The network adapter itself is the beginning of the network connection, in that hardwired or hard-coded onto that network adapter is the physical address of that network connection. It's called the MAC address. And MAC, in this case, that acronym is Media Access Control, MAC. Now, you're going to find, you probably already realize, there's about 3 different utilizations of this same acronym. So it's all specific to the type of use here. The MAC address is pretty interesting. Let me give you an example of what a MAC address might look like here. It is a hexadecimal address. It is actually 48 bits, but it's 12 different characters that make up 6 hexadecimal digits, or 12 different characters that make up 6 hexadecimal addresses here. Let's see. This may be something like this. Let's see. Yeah, we'll just do that. Okay. Now, the MAC address is actually carved up into 2 different pieces here. Okay. You have the first 3 characters of the MAC address that identify, excuse me, that identify the manufacturer. Okay. The last 3 characters of the MAC address is this NIC within the manufacturer. So the combination of all of these characters here combined give me a unique address the world over, and it never changes. It is hard baked into the network adapter itself. Okay. Now, I'm not sure how much you know about hexadecimal. Hexadecimal is a base 16 numeric system. The only values that are proper in hexadecimal is digits 0 through 9 and alphabetic characters A, B, C, D, E, and F. So base 16, and some of the questions you get on your exam they may say, well, which of the following is an invalid MAC address? And what they'll have there is something that is, one of the characters will be H3 or something like that. Well, H is not a valid hexadecimal character. A, B, C, D, E, F, 0 through 9. That's it. So remember that. But like I say, this address never changes. It's the same, and it's hardwired into that network adapter. And like I say, the two different components of it, the first three characters identify uniquely the manufacturer or the vendor of that product. And then the last three is this particular NICS serial number within that manufacturer. So remember that the combination of those is always that unique identifier. And remember also, MAC is media access control. Okay. Now, when I start getting into an environment to where I'm wanting to do full on, come back here, sorry about that. When I'm wanting to do full on networking and addressability, well, routing traffic out over the public internet doesn't use that physical MAC address. It utilizes what's referred to as an IP or an internet protocol address. Okay. Now that's a logical address. Those do change. And most network systems are set up so that when you log on to the session, then you get your IP address assigned to you by a different network security protocol. It's called DHCP, Dynamic Host Configuration Protocol. We'll look at all of that much more detail later on here. This is a clever little tool here, and if you guys have never heard of it or hadn't got you a copy of it, go now and get it. It is a tool called a Wireshark. Open source, completely free tool. It allows me to capture data frames and data packets that are flowing between different networked computer systems. Okay. And when I capture those packets, then it shows them to me up in the top part of the screen here as they're, it'll roll up on that, and whatever packets they're going between endpoints in a computer network, it captures it. Now, a couple of bits of information that even if a data frame is encrypted, that is exposed is the MAC address. Okay. It will show the MAC address from the source computer and the MAC address that is being used to the target or whatever target they're actually sending the packet to. Okay. Now, this MAC address here, that's all Fs, that's referred to as a broadcast address. That means that this computer that's at this address here is broadcasting the same message to everybody in their network or network segment. That's all that is. But the cool thing about Wireshark as well, it's called a protocol analyzer, a network capture utility. You've actually got three different sections of the screen that you can use here. Any of the packets that are captured up top here, okay? If I highlight any of those, it updates information down in the middle of the screen and down at the bottom of the screen. This is where it shows me the binary equivalent of the hexadecimal data that's captured here. And if it is clear text data, if it's not encrypted or encapsulated in any way, it will show me the clear text data over here. Okay. So now Wireshark is not a tool that we get too deep into as far as this class goes, but I will give you, a student shared this with me some time ago. Let me see if I can find it right quick. There's actually there's a couple of links. There was an online tutorial. There's the Wireshark, their tutorial themselves there from their site. Really good too. Sort of breaks it down, good detail stuff. Let me give you the link to that right quick. But there's also a YouTube, actually several different YouTube videos, but one in particular that they shared, which I found very effective. Let me see. There he is right there. Yeah, this guy's really good. I like his stuff a lot. He breaks it down to where, there we go. And Windows. Yep. Show you how to use it to view the traffic on your packet data. Guy is really, really good with his videos. So just check that out sometime when you get a chance. He breaks it down to where even I could understand it. So, but it's a great tool, free to download, free to use, and it allows you to actually view network traffic as you're capturing those packets between endpoints in any network configuration there. So, in your spare time, you guys grab a copy of that, and you'll see what I'm talking about. It allows me to get down and look under the covers, so to speak, of the data. Now, in a wiring closet, there are usually rack-mounted patch panels where the front of the panel, we'll look at that in a moment, that's where your RJ45, the 8-wire twisted pair wires, has the plugs into a port in the front of the panel. Well, on the back side or the inverse side of that, they have this row here of what's called keystone jacks. And what you do is you strip the wiring off of the 8 wires and then punch those down into these keystone jacks. The color coding is very specific. There's actually a particular tool. It's called a punch down tool that is designed to, punch those wires into those individual keystone jacks there. Now, that's in a large wiring closet, large, a panel there. And the other end of this wire could be, it could be anywhere. It could go through different floors into offices, into cube space. And on the other end of that's where you'll have the plug where people will plug their computers into or plug, routing equipment into, whatever. But these are stationary. Once you get these things punched down, they don't change. Now, on the front side of these, it looks like this. Okay. That's where you plug in these are called RJ45 plugs. And you'll see even over here, you got a regular telephone cable plug that's plugged in over there. Some of these are, they have different pieces of equipment where the wiring closet uses fiber optic cables in those plugs. Okay. Now, one thing, and this is just something that just drives me crazy every time I go into a wiring closet and see them missing. Now, that's a pretty well managed cable harness system there, no doubt about it. But what does it look like to you guys that are missing there? Anybody tell me?
Labels?
Yes, ma'am. People say, well, there's labels on the piece of equipment. Well, yeah, great. What if some disgruntled employee on the way out the door just comes in there and disconnects all the cables? Where do they go? I had a situation like that in the same company that we set up the extranet for. I was originally hired in there to do a overall security view. And they liked what we did on that. So about a year later, they hired my company back in there to help them make sense of their wiring closets. They were actually occupied 12 floors in this high-rise building downtown Atlanta. And across those 12 floors, there were 3 different wiring closets. And when I walked into the first one, I came so close to turning down that contract, it wasn't even funny. It looked like the spaghetti factory had exploded in there. There were wires hanging out everywhere, not one label on one cable anywhere. And so I had to have 3 of my employees specifically go through training and get certifications because we had to trace wiring up in the elevator shaft between floors. Okay. So, I'm really glad I didn't turn that particular contract down because it ended up buying my house and gainfully employing a whole bunch of people for almost a year. But it was a mess. And people say, well, there's labels on the panel. Yeah, but no labels on the cables. Okay. So me personally, I want a label on this end of the cable. I want a label on the other end of the cable, wherever it goes to. Okay. Now, these are called RJ45. They're 8-wire twisted pair cable. The color coding is very specific. And then, of course, this guy down here is a flat 4-wire, probably telephone cable over here. So it'll accommodate pretty much, any kinds. I even see here, it looks like some either twin acts or that may be fiber optic cables. I don't know. It doesn't look like fiber optic patch panels. So those are specifically cabling that hooks these patch panels together. So it will accommodate different types of cables. Now, in your switch is a device that allows me, and we'll go over to this area here. A switch is what allows me to consolidate many different computer systems into a singular controller, switch type of appliance. The old versions of these guys used to be called hubs or bridges. They were not intelligent, had no intelligence whatsoever. I have actually a 5-port hub sitting on my desktop here. I've got 3 of the computer systems in this room that are hardwired to my router, which is down in the great room. But they just all are plugged into this hub box here. Now, these are the older systems, the hubs and bridges were what referred to as broadcast domains, in that anytime anybody transmitted any information into whatever port they were plugged into, the hub just broadcasts that same packet to every port on that hub. Okay, now the newer switches don't do that. They utilize what's referred to, and they saw it here, they call it a CAM table, Content Access Management Table. Okay, and it keeps this table inside of the switch, and it says, okay, here is the MAC address of the computer that's plugged into this particular port number 0. Now, of course, this is just representative to the MAC address. That's not a valid MAC address, of course, but the CAM table actually tracks that, so that if I'm on port number 0 and I want to communicate with the computer that's on port number 5, well, I don't broadcast that communication request to every port on the switch. It broadcasts it into this intelligent part of the switch. It says, oh, okay, the MAC address that you're wanting to communicate with, BC, they're plugged into port number 5. So it establishes that port-to-port connectivity between my computer and the other. Okay, so it's not one large broadcast domain anymore. And the switches, they got very intelligent, and we're starting to see as well quite the aggregation of functionality too. The next wave of these managed multi-layer switches, I think, and there's a lot of engineers I think along these same lines, that they are beginning to aggregate the switching and the routing and the gateway functionality all into the singular appliance. These appliances also have the capability of sending power right down these Ethernet cables. It's called PoE, power over Ethernet. So in addition to the network traffic of transfer of data, they can also send power signals down those same lines as well. Okay. So much more intelligent on the way that the switches operate now. They are very high speed. I was telling you earlier, even the lower level modular departmental level switches are operating at a bare minimum of 10 gigabits per second. Some of them are 20, 30, 40, 50 gigabits per second. That's what these guys look like right here. Now, the unmanaged switch, the hubs, they call them, just plug a device into it and it starts broadcasting data, send or receiving data. But it's a large, what they call both a broadcast and a collision domain, meaning that everybody's vying for the same communication capability. So you end up having data collisions a lot. And it broadcasts every message to every port on that switch. So there's a lot of traffic there. And, if I'm on a switch like this, and it's not the managed switch, say if this computer here broadcasts a message in, will it broadcast it to every port on that switch? And everybody else, all the other computers have to say, well, is that message for me? And if it is, I'll respond to it. And if not, I just have to ignore it. But I have to address each and every one of those. So quite a bit different now with the new managed multi-layer switches. These things are rack mountable, stackable. You'll see them in these large racks. Looks like this. These large racks here where you'll have multiple switches mounted up. They all then communicate upline typically to what's called top of rack switches, very high speed switches. And then even those will then communicate upline to these super high speed type of rack switches. And it just consolidates all of the wiring into a singular screaming high speed component that typically then is hooked up to a router downline somewhere. But I'm telling you, we are starting to see that aggregation of the switching, the routing, the gateway function, and so on. Yes, Sloan, I see that hand. Go ahead.
I have a question about switches versus patches. I think I'm not quite understanding why, like personal computers and stuff, would it be directly wired to the switch instead of going through the patch?
Well, we can do it. You can do it either way. The difference is the patch, the hub device they call it. They don't have any intelligence at all. It's just this large broadcast domain. It still will pass through the signal, but the switch is much more intelligent movement of traffic. And going back to say, if you've got everybody, let's go back here. If you've got everybody in, let's say, 2 or 3 or 4 different departments that are all hooked up to the same switch, okay? There is other things that I can do with these switches to even further segment those. But the switch does intelligent switching. So rather than broadcasting that message to every port on that switch like the hubs do, okay, or the patch panel does, it is intelligent port-to-port communication directly from one computer to another computer. So all the other computers are not hearing all that noise, all that traffic that's not meant for them. Okay.
But you
So
do need the patch, though. Are you saying you need the patch, and so the switch
No.
is the optional thing? Okay, got it.
the switch sort of incorporates the old patch hub and the router and the switch functionality into a singular appliance.
Okay, thank you.
Yeah, and thank you for the question. I appreciate that. Another really cool thing about these managed multi-layer switches, and we don't really get too deep into it in this class, but it's called virtual local area networks, VLANs. And these switches, the largest one I've ever worked with personally had 48 ports on it. Okay. Look like one of these guys here. Now, let's say that I want to really cut down on the total pieces of equipment that I have deployed out in my office building or my business or whatever. I can use one singular piece of equipment and replace all of those other pieces of equipment. This, in essence, becomes my wiring closet. Okay. Now, I want to further isolate and secure the individual computer systems. Although they're all plugged into the same piece of physical equipment, I can go into the command language of this intelligent device and create what's called a VLAN, a virtual local area network. I configure a VLAN on that system, and I'll say, all right, I'm creating VLAN 10, virtual local area network number 10. So I'm going to take the computers that are plugged into ports 0 through 7, and they're going to be isolated in VLAN 10. So I'm then going to take and create VLAN 20, and I'll take the computers that are plugged into ports 10 through 14, and those are VLAN 20. That might be the HR department. VLAN 10 may be my CSRs, my customer service reps. Well, normally in a switched environment, anybody that's plugged into that same switch can directly communicate with anybody else plugged into that same switch. If I further isolate them into their own virtual local area networks, it's like I had the HR department isolated in another building behind a firewall, behind their own equipment. So they're much more secure. I can wrap additional layers of security around them. I do the same thing now with these managed multi-layer switches because it logically isolates them. So if somebody in VLAN 10 wants to talk to somebody in VLAN 20, they have to go through a router and a gateway device, which is another layer of security, you see. So even though they're physically configured on the same device, I can further logically divide them up and put additional limits and layers of security around those individual connections. Very cool environment there. And it's a double whammy. It allows companies to cut down on the individual numbers of pieces of equipment required, but also give me that departmental type layer separation, as well as the additional layers of security that I can wrap around those individual VLANs. Very cool environment there from a networking perspective. Now this sort of looks like some of the command language and the down inside of the managed switches. It's sort of a log that tells me, whatever's going on with what port the information is coming from, what port it's going to, information about speed of individual ports. It's like a system log for the switch itself. Okay. There's also down in that underneath the covers there in these switches, quite a hefty command language that will allow me to, well, one of the things is create those VLANs, those virtual local area networks. This also gives me much the same type of information that we saw with the Wireshark tool, capturing data frames and packets. Only here it shows port to port, but it also shows me the content of the makeup of the data packets and the data frames, the size that they are, things like that. Now, this is what I was telling you about the power over Ethernet. Now, one of the first times I ever saw this implemented was with security systems. And you guys can go to Costco or Sam's today and buy one of these security systems. The hub device is actually one of these managed multi-layer switches, and they also build in typically the recording function, the DVD recorder into that box as well, or if it's a chip-based recording, whatever. But what it enables is, rather than having to run a wire out to the corners of the building, with the wire that plugs from the control unit, the switch to the cameras, and then running an additional power cable to those cameras. This does it all with a singular cable, and it's the Ethernet cable, the 8-wire twisted pair. Friend of mine that he's retired now, but he worked with IBM, and I think there were a couple of telcos in there, maybe T-Mobile and AT&T perhaps. But he worked on the original construction of the Mercedes-Benz Stadium here in downtown Atlanta. And he said inside and outside the perimeter of that stadium, he said there's about 1,000 miles of what they call Category 7 Ethernet cable. And they use this all over the stadium. They've got these little display panels. They've got all kinds of sophisticated security cameras and setups. So the signaling is run through these high-speed Ethernet cabling, but the power is too. And in that particular environment, they're using this specific version of it here, this standard 802.3AT. It's called PoE Plus, or Type 2 Power over Ethernet. That actually will deliver, it can deliver actually up to about 30 watts, 34 watts of power down the Ethernet cable, the same networking cable. Doesn't require an additional power cable. Okay. But that can drive security cameras. And I'm talking about sophisticated zoom, tilt, pan, night vision, or a small display device, whatever. And the switch actually that it's plugged into is what generates that power. And it's wattage, and it's actually 48-volt power, but still plenty enough power to drive those very sophisticated security cameras too. The high end of that Type 3 and Type 4 is the 802.3BT, they call it. That goes up, I mean, it's on up into like 45, 50 watts at 48 volts. There's a newer version of it. I think Cisco is the one that's been experimenting with it. They're talking about pushing the envelope on up to around 60, approaching 70 watts of power down the existing Ethernet cabling there. Okay. Now, I will tell you the standard range on the most Ethernet Category 5, 6, and 7 cables, the standard range on those things before you start getting that, what we talked about yesterday, the signal attenuation, is about 100 meters. Now, the faster speeds you're pushing down those, and the PoE type you're pushing down those, well, that cable length gets shorter. So it will successfully carry those, not only the networking signals, but the power signals as well. The PoE switch has to have and if you're going to be going beyond that attenuation cable length limit there, they have these in line, they call it power over Ethernet injectors. It's like a power booster in line that are put in place there. So that's some of the networking equipment. And remember, it all begins with the network interface card, the NIC, or the network adapter, which is plugged into the computer system. Don't forget that adapter is what contains the physical MAC address, never changes. Okay. When we log into the network, we pick up the internet protocol address, the IP address, typically dynamically assigned by the dynamic host configuration protocol server there. Okay. Remember the switch, the hub device is the non-intelligent passive kind of hub. Any computer that's plugged up to any of those ports broadcasts that message out to every other port. Okay. The managed multi-layer switches, they call them, much more clever management, port-to-port communication. Oh, another thing about that port-to-port communication too is most of the switches, and the switch has to support it, but almost all the modern ones do. When I establish when the MAC table or that says, yeah, you're on port 0, the computer you're wanting to talk to is on port 15, it does a port-to-port connection and uses a minimum of 2 data channels. So it's full duplex communication, simultaneous communication, both directions simultaneously. The old hub devices, most of them were not capable of doing that. Remember these versions, the IEEE standards of the power over Ethernet. In your workbook, they'll tell you what the specifics are as far as the low end and up end power that these things will actually drive. And know too, the development on this is very dynamic. They're increasing that power push almost on a daily basis with the major manufacturers there. So, but that's that base level equipment. Okay. Now, any questions on that before we move along? All righty, let's get on into it. Nolan, I see you have joined us here. I'm guessing as an audit student. Welcome to the party. And I also welcome you to participate if you wish. If you have a question that comes to you while we're going through the lecture here, you feel free to jump right in and ask that question. You can use your little raise your hand icon. You can type it in the chat box, or you can just turn your mic on and talk to us. I welcome that. I do not consider those interruptions. I consider it an opportunity for myself and you and maybe somebody else to learn something. So,
all right, thank you.
Yes, indeed. Now, we are starting to see, as I was talking about earlier, much more adoption, I guess would be the best way to put it, of fiber optic cabling from a network perspective. However, there is still lots, especially internal in networks, of this twisted pair cabling from the wiring closet out to the hubs or switches and then on to individual computer systems. Let's see, I've got 1, 2, 3. Yeah, I've got 3 hardwired Ethernet connections in my desk here. And then from the hub, I've got 1 Ethernet cable that goes down through the flooring and ceiling, and then it plugs into my router gateway box, which is down in the great room. The other systems are wireless connectivity, and I've got, I guess, one more. One more that is down close to the box that is actually hardwired directly to it. The unshielded twisted pair, and I'm telling you just don't hardly see this much anymore, mainly because of building codes. The unshielded twisted pair, that's the old dull gray PVC coating around it. Doesn't have any grounding protection on the inside. It actually acts as a vent for airflow through that thing. So if it burns, it's just a burn tube going through there. Another thing that a lot of this has been outlawed in some of the new construction, especially, is because when that PVC coating burns, it releases these very noxious gases that kill us human critters. But the configuration of the wiring, regardless of whether it's unshielded, shielded, or even what they call plenum cabling, the color coding is the same. The twist pattern is the same. What you get, the major difference is whether it is shielded or and the type of shielding that you have in there from a grounding perspective. The color coding on the wires, same across the board. Finally, when I first got into networking back in the dark ages, there were about 3 different companies worldwide, and they all had different color coding standards for their 8-wire twisted pair. Finally, there were a couple of companies got together and laid down the law on this. It was organizations, not companies, but there's 2 organizations, one known as the EIA, the Electronics Industry Association, and the TIA, the Telecommunications Industry Alliance. They finally established the framework and the standards for this stuff. So you got solid orange wire, orange and white stripe wire, solid green wire, green and white stripe wire, solid blue wire, blue and white stripe, solid brown and brown and white stripe. The orange and the green wires are the ones that are utilized for doing the transmit and the receive signals. Okay, they call it RXTX, receive and transmit. The twist pattern on these things, I was taught as a young whippersnapper engineer that we needed to have around 10 to 12 twists per inch. And the twisting is important because it's designed to cast off cross wire interference. Okay, electromagnetic interference and even radio frequency interference can cause problems with these. I have seen engineers, when they were putting the ends on these cables, they would untwist it back for half an inch or so, put the ends on, and and they had that untwisted wire. Well, that just invites interference. A lot of that cross wire interference, call it alien crosstalk. So it's just interference in general, and that twisting, that tight twisting of those twisted wire pairs there is designed to block against that electromagnetic interference protection there. This is the shielded twisted pair version of that. A couple of clever things here. First, the aluminum shielding around the wire, okay? And it's gooey, sticky kind of aluminum shielding there. They have the common ground wire here that is utilized inside of switching equipment into a common ground. And then this little clever piece right here, this is just, they call it cladding, or it's like fiberglass roping or something like that. Well, here's the deal on that. If you have ever tried to use a razor or a sharp knife to trim the cable or to trim the casing down because I needed more wire exposed, there is no way that you can do it without cutting into some of these wires. Okay, it's just darn near impossible. So this little clever guy right here, if I need to strip this cable back from here to here, right here, I will make just a slight little cut in that PVC casing there, and then grab this fiber wire and strip that bad boy down. And it works like champ, works like a razor blade, but it does not cut into the wiring and expose ground out possibilities. Okay. So now in some of the higher quality ones we find, in addition to this aluminum sticky wrapper around here, the shielding, you also may find the same thing as the coax cable, the braided copper around that. Now that's pretty high quality stuff and not typical for RJ45 or Ethernet 8-wire twisted pair cabling anyway. Okay. But that's pretty good configuration there. So shielded, additional ground. This is a chart that were I would memorize it. What it tells me is the category, and the category typically implies out of the 8 wires in the cable, how many of them are actually used. Okay, Cat 5, 5E, 6, 6A, 7, and 8. You will also see, as I was telling you earlier, that for the category 5 and up, The maximum distance on those things before you start expecting that signal attenuation or weakening is about 100 meters. Now you'll notice here we've gone from 1 gigabit per second to 10 gigabits per second on the Cat 6, and you see that the attenuation length is cut almost in half. Okay. Same thing down here when we start getting into the Cat 8, 25 gigabits per second, 40 gigabits per second. You got about 30 meters there rather than the full 100. So those are the kind, and especially the guy here, 100 gigabits per second on the Cat 7, got about half of the size, half of the, well, in this case, about 15 meters, about 50 feet total here is what you run into. Okay. So very short for the specific category implementations there. I would make flashcards here. This is the nomenclature that they assign to each of these. 100 base TX. Anytime you see a T in this last part of the naming standard, that tells you that it is copper cabling of some sort, and more than likely twisted pair copper cabling. Okay. 10G base, that is your gigabit base. Okay. T, still copper cabling, twisted pair. Okay. So flashcards, learn that and be able to recognize with a Cat 6 cable, which version of the Cat 6 cable only has about half of the attenuation length. Well, that would be the 10 gigabits per second. The 10G base Cat 6. Okay. Only about half of what you get out of the others. Now, I talked about EIA, TIA. Yeah, they are the ones that sort of laid down the law on the standardization of the color coding. And it's set. There's actually 3 different flavors of the ends here that we'll talk about. If I am going to be doing what's called a same kind of system to same kind of system hookup, you know, a PC to a PC, a router to a router, a switch to another switch. I have a very specific cable. If I'm going to be hooking up different types of equipment, a PC to a switch or a PC to a hub, you know, I have a very specific type of cable. For the second one I talked about, if I'm hooking up a PC computer to a switch, I use what's referred to as a straight through cable. Okay. Meaning that it is wired on both ends of that cable exactly the same way. In this case, I would use the 568A standard from the EIA TIA. Pin 1, green and white stripe. Pin 2, solid green. Pin 3, orange and white stripe. Pin 4, solid blue. 5, blue and white stripe. 6, solid orange. 7, brown and white stripe. 8, solid brown. Both ends of that cable, I want them to be wired just like this, called a straight through cable. And remember, it's to hook up different types of equipment, a PC to a switch or a switch to a router. Okay. Straight through cable. Now, if I'm wanting to hook up the first example I gave, I'm wanting to plug up one PC to another PC or one switch to another switch, I typically utilize what's called a crossover cable, where I have one end of that cable wired with the standard A standard and then the other end wired with the B standard. Notice what it's doing. It's switching the transmit and the receive orange and green wire sets. So it acts like what's called a null modem. Okay. It is switching over the transmit and receive ends. So it thinks it has a modem in the middle of those two. Okay, so that's called a rollover cable. Okay, now I'm sorry, that's called a crossover cable. Crossover cable, 568A on one end, 568B on the other. Now the rollover cable is utilized for instance, plugging up my PC into the management console port on the back of a switch or a router or a firewall or a gateway device of some sort. All your switches, all your wireless access points, your routers, they have a console management port on the back side of those things, which allows me to go in and configure it in essence. Now, most engineers nowadays are just using the wired connection and dialing it up with its IP address, not physically plugging up to those things. But if you do, that's where you want to use the rollover cable. On one end of the cable, it's 568A wired, and you just roll over all the wires on the other end. Pin 1 goes to pin 8, 2 goes to 7, 3 goes to 6, 4 goes to 5, just rolling over those wires. Okay. So that's for the management console cabling. Now, all that being said, I will tell you, for most of the modernized equipment, switching equipment, routing equipment, it does that crossover for you. But once again, read the instructions before you start working on those things, and it will tell you if you need a crossover cable as well. Some of them do, some of them don't. When I and my engineers that work for me, if we were going out in the field to do work, I always made absolutely certain that they had 2 known working copies of each one of those 3 cables, 2 known working copies of any power cables that may be used, any kind of interface cables or anything, 2 known working copies in their bag. So most of them, in addition to the tool bag with all their tools, they had a cable bag that went along with them as well. Okay. Now, this is typically what's referred to as your RJ45 cable, the 8-wire twisted pair. We have also seen this same connector here used, but with the new 4-wire telephone cable called RJ11. Same width on the cable, only it only uses the middle 4 connectors. Okay, so and then of course some of the RJ11 connectors is only the 4-wire wide anyway. Okay. All right, Alma, I see you have also joined the party. I want to welcome you as well.
Hi,
And
thank you so much.
Thank you for dropping in. And I want to encourage you, if you want to, feel free to jump in and ask questions while we're going through the lessons here. And I welcome those. So welcome, relax and enjoy yourself, and feel free to participate.
Sure, thank you so much.
You bet. Now, here is one of the tools that you really need to have in your toolbox. The one that I keep saying, the one that I have, the one that my son now has in his toolbox. It's a wire stripper. It is a wire cutter. And it is also this next tool we look at. It's called a crimper. And the crimper tool actually allows me to install the ends on the different types of wires. RJ45 wires, RJ11 wires, coax wires, even some of the crimpers. Mine didn't, but there's some of those crimper tools that also will allow you to crimp fiber optic cable ends on as well. Okay, but as I was telling you guys yesterday, don't crimp on your tools. Okay, get high quality tools, and you will thank yourself for it on down the line. This crimper part of it right here, that was something that's designed for crimping on our, coax cables, that kind of thing. But the combination of this and this is sort of 2 in 1. There's that punch down tool I was telling you about earlier, that punches down into the wires down into the keystone clips there. And that's either for punching them down into the back of the patch panel in the patch room, or punching them down into the wall sockets, on the back side of the wall sockets that people plug their computer systems into. Okay. Okay. Alma, your mic is still hot there. You might want to mute that. So, and now this, I showed you guys yesterday, the power supply tester. Same thing with this guy here. This is actually one version. It's called a cable tester. You plug the cable into both ends of these pieces of equipment. Both of them are battery operated now as well. And it sends a signal down each and every wire in that cable, and it will tell you if the wire is good end to end. Most of them utilize not only LEDs, but also audible sounds that let you know that the wire is good end to end. But it'll help you track things like say if you got one wire that is crimped or broken in the 8-wire set, it'll tell you approximately how far down the wire it is in some cases. Okay. Now, what is not shown here is this. They call it a toner probe. We call it in the industry, we call it a cat and mouse. Same kind of thing. It's two pieces or one unit that actually transmits an audible sound down a cable. And then there's a probe that you can track that sound through the cabling, even through walls, through ceilings, in the elevator shaft, and find out where the other end of the cable is. Okay, so the cat and mouse is something that you got to have. I'm going to have to get a good image of those and put it on this same slide as well. I see they didn't do it at CompTIA. But the same as with the PSU, these things run on batteries. Make sure you have replacement batteries in your tool bag before you go out into the field. Okay. That was so frustrating when I found out in the middle of nowhere and couldn't find the batteries. Here's another little clever connector here. If I wish to check a network connection without my system being plugged into a network, I can make this called a loopback plug. And you'll notice what it's doing is the same thing as the switchover plugs. It is switching the transmit and receive, the orange and the green wires there. Now, the suppliers, the company that sells you electronic equipment, they'll sell you one of these for, I don't know, $4.50, $5, maybe even more nowadays. Or you can build your own just like that. Get you a handful of RJ45 plugs, a couple of pieces of about 4 inches of orange and green wire, and wire it up. Pin 1 solid orange, pin 3 orange, solid orange, pin 2 solid green over here to pin 5. And that crosses over that transmit and receive. So you plug that into your network adapter and it thinks that it has a network connection. So you can test network connectivity without actually being hooked up to a network with that loopback plug. Okay. But make your own. I mean, don't spend $4 plus just for one of these things when you make your own. The on your switch devices, the newer managed multi-layer switches, all of those, I was telling you, they don't broadcast every message from every port to every other port. Okay. But there are certain times when I want to be able to hear and to read all of that. On the active multi-layer switches, they have what's referred to as a tap or a mirror port. And tap is test access port, TAP. So if I plug my computer into that mirror port or the test access port, I can intercept and capture every data frame or every data packet that's being broadcast on any of those ports. Okay. So, and the, major difference on that, I can, in the passive mode, I'm just reading what's going on there. I'm not doing anything to it per se. In the active mode, I can not only monitor that traffic, but also capture a copy of it that I can analyze later on if I wish. Okay. So, and all of the new managed multi-layer switches have that mirror port or that tap port, they call it. Okay. So now I talked about the two basic types of cabling. I talked about the unshielded twisted pair, they call it UTP. And those are the ones that you'll see are the old dull gray PVC coating. You really don't see it much anymore, especially in new construction anyway, because of its danger and it burns and releases the noxious gases. The shielded twisted pair it's been upgraded quite a bit, but it's still using these composites on the PVC coating, and those are usually ones you'll see that are the bright blue coating there. It is more fire resistant, but it will burn, and it does also release the noxious gases. There is a upgraded version of it, and the graphic that we saw that had all the bright orange cables plugged into the patch panel, those are what it's referred to as plenum rated. Now, plenum is a term that if anybody that's ever dealt with or worked even in the HVAC world, heating and cooling, plenum space defines just about anywhere that air moves around a corner. Okay. We find too, especially in new construction, that oftentimes the HVAC people, they'll come in first after the electricians, have studied, or the builders have studied the place out. The electricians have run their wiring. And then the HVAC people, usually working up top, they have their venting space and so on. Well, then oftentimes the networking folks will run their cabling very close to, and sometimes in the same venting space or the same carved out area where the HVAC vents are going to go. And that's dual purpose. I mean, it separates it from the power cabling so you don't get any hum or feedback, electromagnetic interference from the power cables. But it also isolates that cable up into that area. Very nice bends and easy to manipulate it in there. Now, sometimes the building requirements require this, what's called plenum rated cabling. It is fused, the ends are fused into the cable itself, so you don't have that natural airflow. It is grounded, and it is the PVC composite that is the wrapping on that is fire resistant. It'll melt, but for the most part, it won't burn. So it doesn't release the noxious gases that oftentimes get picked up in the HVAC ducting and end up killing us human critters. Now, there's also times, and we've seen in different types of configurations, different installations, to where it's required that the cable is buried underground. Well, if indeed that's the case, you just got to make certain that it is weatherproof, weatherized, so to speak. I have run cable on the outside of buildings before, and we always ran it inside of, at the very least, PVC. So it's protected from weather. The least little nick in some of this cabling and just one little drop of moisture can ruin a whole run of cable in very, very short order. So it needs to be protected. It needs to be weatherized. And you got to make certain that you are selecting the proper rated cabling for the installation that you're going to, because there's a lot of localized building codes that are very particular on the kind of cable you may or may not run. Here's our old trusty fiber optic cabling. Fiber optics is an interesting, the technologies have advanced, just in my opinion, light speed over the years. Way back in the day, the very first fiber optic cabling I was ever involved with installing, the cable itself only had a bend radius of about 30 degrees. Okay. If you went beyond that, you were going to crack that center core because it was solid glass. The center core was. Now they're using composite materials, glass, plastic composites. And I was just blown away when the engineer came and installed my fiber optic here at my home. And it's been a couple of years ago now. Of course, they trenched around from the street, trenched around the side of the yard, down under the deck, came up the wall, and that sucker went almost 90 degrees with that cabling through the wall. Through the wall, plugged it in right into the router box itself. I'm just blown away. And he was the one that was telling me that the cabling now is being manufactured with several different mixtures of composite materials because it's flexible, just very flexible. So they're not terribly worried about breaking that solid glass core anymore. Now, there's two different flavors of fiber optic cabling. Primarily, there's several more, but two major ones. There's one called single mode, SMF, they call it, single mode fiber. And then there's multi-mode fiber, MMF. The single mode fiber is just that very, very thin single core. It runs anywhere in the neighborhood of 12 to 15 microns, which that's about a third the size of a human hair. Very, very thin, right? And those are typically designed for very long haul, long distance runs there. And the switching equipment on those more than likely uses a pure laser for the light signaling. Now, the multi-mode fiber, it is thicker. The microns on anywhere from 30 to 50 microns thickness, and they're designed to simultaneously carry different light frequencies down the same core, just thus sending and receiving multiple bits of data simultaneously. Okay. Now, fiber optics, just like copper cabling, can transmit data in both directions, but only one direction at a time. So more often than not, you'll see these things set up in dual mode, where they're running two wires, okay? And some of them have the two connectors in a singular enclosure, but it's two different fiber optic cables, one to transmit in one direction, one to receive in the incoming direction. And these guys here, the naming conventions on these are pretty interesting. This is called straight tip, the first one here. Okay. The next one down is called let's see, straight tip connect. Well, senior moment there. Hold on. The last one here is called either local or lucent connect. Okay. And I just drew a blank altogether there. For the life of me, I can't remember what the second acronym there is trying to tell me. SC, it'll come to me. Straight tip.
Subscriber.
Say again? Subscriber connect. Yeah, I'm sorry. Yeah, thank you, ma'am. I appreciate that. I don't know why I blanked out on that. Yeah, subscriber connect. And of the ones we see here, these the two that are shown here, the straight tip is the one that is not shown here. It is a connector that very quick connect. It's push and twist. Okay, and there's even a version of it called multi-mode or multi-miniature or sub-multi that is designed for underwater use. So, but it's a very quick connect. It's a push twist, you're done. These guys here, you'll notice, this is the subscriber connect, this first one here. That's this guy right here. Okay. And sort of a squared off connector there. That connector is about the same size, not quite, but about the same size as the RJ45 8-wire twisted pair connector. And you'll see it right here. It's got the clip that sort of clips into the equipment there. This is the lucent or the local connect, and it has this kind of, the springy kind of connector there. The straight tip or the standard tip was one of the very first ones we started seeing. Now, these are just about the two that you see for the most part in newer equipment, the subscriber and the lucent or the local connect. Okay. And more often than not, now you're seeing them rather than just a single wire or the single ends, they're running dual wire inside of a singular component there because that gives you that duplex communication dynamically there. Okay. This is your coax. Coax comes in also two flavors. It comes in what's called thick net and thin net. And the difference is the diameter of the cabling. This is thick net. It typically uses what's called an F-type connector. That's this guy right here. And that's the one that screws into the port itself. And then the thin net uses what's called a BNC, a bayonet Neil Conselman connector. And it's the same thing as the straight tip fiber. It's a push, twist, and you're done. Very quick setup and tear down. But the configuration on either one of those thick net, thin net is exactly the same as this. Okay. You have the single copper strand in the middle. You have the rubber plastic composite that goes around that. Then you have your first aluminum type of shielding. And then I'm guessing this has been the very first. I'm trying to think when the time was. I'm trying to think back when Ted Turner first started introducing us all to satellite television. One of the first versions of coax cable I saw, it didn't have this braided mesh around it. It had just strands of copper wiring there that was the grounding component. And I got to visit a company, it was over in Holland, that actually makes this braided copper. And man, you ought to, it's a loom is what it is that braids this stuff, much like a thread loom, you know. Fascinating to watch, I'm telling you. But that not only provides some additional strength and electromagnetic interference cast off, but that is the common ground as well. There's the hot lead, there's the ground lead. Okay. So regardless of whether it's the thick net, which is about a 1/2 inch diameter, or the thin net, which is about 1/4 of an inch diameter, the configuration is identical. It's just the ends, either the F-type ends or the bayonet neoconstable B and C type ends. Military cats are very familiar with the B and Cs. Setting up networks out in the field, they want that quick setup, quick teardown, push, twist, you're ready to rock. Okay. So that's very common still in remote installations like that. Of course, even more common, we're starting to see it now, is the wireless networking out in the field too, rather than the wired networks. So remember the twisted pair. Remember the color coding there. Remember those 3 basic types of cable: the straight through, the crossover, and the rollover cabling, and the implications on all 3 of those. You'll get a couple of questions about cabling in general on your exam, but they do a pretty good job of helping you along the way with those things. And I'll tell you one thing, and I didn't mention this yesterday, should have. And you guys may have even picked up on this when you're taking your individual lesson quizzes. If you really, really pay attention to the verbiage that they present the question with on your questions, and then you read all of the available answers prior to making a selection, you're going to find in many, many cases, the verbiage of the question itself is leading you to the correct answer. Okay. But you really got to look for those little triggers there in the Q&A stuff. Okay. All right. Now I've had you guys strapped to your seat now for about an hour and a half. So I tell you what we're going to do right quick here. And you folks that are joining us either on YouTube or that have jumped in to audit the class, just hang with us. We're going to take a very quick morning break. I would like everybody to, if you would, keep the break to only about 10 minutes. That'll give you, I think, plenty of time to jump up and take a quick latrine break or to refill that coffee or juice cup. And we will be right back and pick right back up where we left off. Now, before I pull the trigger on this, does anyone have any questions at all before we go ahead and take a quick break here? All righty then. I will see you all back here shortly, and we will have some more fun. All righty, folks, let's get ready to re-engage here. What do you say? All right. Okie dokie. Let's dive on back in this sucker here. Now, we talked about the wireless networking environment. We talked about, the switches, the managed multi-layer switches. We're seeing lots of those, as a matter of fact, that are once again being utilized to sort of aggregate and incorporate multiple functions into a singular appliance. And we're seeing it more and more, and there's quite the hybrid connection of wired and wireless type of networks, and especially with the inclusion now of these mesh type networks that are using the 6 gigahertz wireless connectivity, like your Alexas and your Siris and those kind of voice control mesh kind of network appliances there. So it's quite the hybrid approach. The wireless networking environments in general are being used more and more often. Now, many, many moons ago, well, actually not that long ago, as a matter of fact, when we started seeing these wireless appliances introduced into home networks, the Soho type of networks there, the access point, the AP, the WAP, they called it, the wireless access point, was sort of the centralized hub, if you will, that all of the wireless appliances, especially in homes, in home networks and small office, home office networks, that was the DMARC, the entry point for the networking coming from the internet service provider, whomever it might happen to be. And originally that was delivered into these boxes by way of a regular telephone line. Your analog 4-wire telephone line come into the back of the box, and then most of them would have an Ethernet, an 8-wire twisted pair connectivity from that box into a router, which would then feed, other systems inside the environment as well. Now we're seeing that composite and aggregation of all those functions into a singular appliance. Now, I want you to think about these systems along the lines of what's referred to as the starting point anyway, is called a basic service set, a BSS. The basic service set consists of the wireless access point itself and all of the wireless appliances that are communicating directly with it. Some of the wireless access points now we see still have the exposed antenna on the outside. Most of them don't, as a matter of fact. Even the coax cable boxes, we're seeing those that are standing up, vertically, and they don't have the exposed antenna. The antenna is still there, but it's a unit that is around the inside enclosure of that device as well. The identifier, the unique identifier of each one of these, what we call the BSS, the basic service set, is the MAC address of the device itself. Now, remember, the MAC address is associated with the network adapter. Every one of these has a network adapter built into it. And every one of these has a unique MAC address, that 6 hexadecimal character address that we looked at earlier. Okay. Now, if you take multiples of these BSSs and hook those together, then that constitutes what is known as an extended service set, an ESS. So maybe you've got one basic service set that provides access and connectivity to the HR department. You got another BSS that provides connectivity and access to the customer service reps and the accounting department. Well, then all of those can be set up hierarchically to communicate either wired or wirelessly upline to a controller, a wireless controller box. And then the controller and all of the components that make up the individual basic service sets constitutes what's referred to as an extended service set, an ESS. Now, all of these hierarchical approach to it, the standards, the frequencies that the wireless access points utilize, those are all defined by this set of standards called IEEE 802.11. Now, the very first introduction of a wireless access point was 802.11a. It communicated only with the 5 gigahertz frequency band, and it was the very first entry into the wireless access point world. Now, the frequency bands that are utilized on these things have expanded quite a bit. The second version, 802.11b, utilized the 2.4 gigahertz frequency band. Now, there was a problem with the initial 5 gigahertz in that at about the same time that the wireless providers started putting those things in homes, there were a couple of mobile cordless telephone handsets that were introduced at about the same time, and they also were using that 5 gigahertz band. So, and the first couple of versions of it, they didn't have the auto channel select on those things. So sometimes people would set the mobile phone and the wireless access point to communicate over the same channel, and they would get some interference and some interruptions on those. Now, and then actually shortly after that, they started putting the 5 gigahertz band. There's actually 23 different channels associated with the 5 gigahertz bandwidth. And most of the devices auto select. They'll, if one channel they're on is noisy or getting interference from other devices, they'll automatically switch over and check to a clear channel. The modernized devices that we're seeing nowadays actually utilize all 3 of these frequency bands. They'll have the 2.4 gigahertz frequency band range, which there's actually 14 channels available there, but the FCC, for a couple of reasons, I understand they limit that utilization in North America to only the first 11 of those channels, and those channels actually overlap one another, actually 5 channels deep, so you get cross channel interference on those. But the same appliance now uses all 3 of the different frequency bands. The new 6 gigahertz, that's frequency band that's utilized for some of these home mesh control, voice activated mesh control networks, like the Alexas and the Siris and other manufacturers there as well. The 5 gigahertz frequency, when it first came out with 11A, it was 54 megabits per second. It utilized a frequency modulation technique called DFS, dynamic frequency selection. And then after the first couple of versions of it, it got where it was truly dynamic. It would select different channels based upon if one channel was noisy, it would go ahead and select a different one there automatically too. But we did start having the original problem with other devices that were interfering with that. So shortly after that, they introduced 802.11b, which was a 2.4 gigahertz. Problem was they bumped the speed on it down to 11 megabits per second. Now, later on, they introduced a different version of the 802.11. It was called 802.11g. Now, they did bump the range back up on that as far as the speed to 54 megabits per second, or it was selectable. If you had an older 802.11b system, then the G would communicate with it, but it would drop back to that lower 11 megabits per second. It utilized the dynamic spectrum as well as a new version called orthogonal frequency distribution modulation, okay, or frequency detection modulation. Just a different way of the frequency modulation on the signaling itself. But it was the 2.4 gig range. Now, I was telling you about the overlapping channels. If you look at the 11 available channels that we are allowed to use in North America, the channels overlap one another as far as the signaling, 5 channels deep. So if you're going to be setting up like 3 of these in the same location, for instance, to service, multiple people throughout the enterprise, you want to maintain that 5 channel separation. Set the first one up on channel 1, second one up on channel 6, third one up on channel 11, So you don't have that cross channel bleed, alien crosstalk, they sometimes call that. So that was the major issue that we have had all along with 2.4 gigahertz. Now, I'll tell you something about 2.4 as opposed to 5 gigahertz. 2.4 gigahertz propagates very well through solids, through walls, through forests, through over, under, around, and through, towers and mountains and stuff like that. 5G just does not. It just does not propagate well through solid walls. It's very fast. It is massive bandwidth capability, but you just about have to maintain line of sight with the 5 gigahertz, and in some cases even the 6 gigahertz signaling, because it just doesn't propagate well through solids. Now, the system that I have in my home here, the one I was telling you about, it does all three. It does 2.4, 5 gigahertz, and 6 gigahertz, and it is very powerful. It propagates pretty well in any of those frequency bands. 802.11n is one of the later ones that we've seen introduced here. It is dual band. It does both the 2.4 and the 5 gigahertz. It has a clever little function here called MIMO, multiple input, multiple output, and it also allows us to bond two channels together, thus increasing the communication speed. Now, it also uses that dynamic frequency selection for the 5 gigahertz band ranges. The 2.4 gigahertz still doesn't do dynamic channel selection, but the 5 gigahertz does. But it's very fast. I mean, very fast. A half a gig, 600, 500, 600 megabits per second communication there. Right? It's also capable of being very tightly secured. It can use even what they call encryption tunneling protocols, they call those. So it's capable of being set up to be very, very secure. This is the one here that I have, the new one I have in my home network here. This 802.11ax. It's all three bands. It's your 2.4, 5 gigahertz, and 6 gigahertz band ranges there. Very fast. It's pushing hard on a couple of gigabits per second. So very, very fast frequencies. Now, the speed of the ranges on the different frequencies is much higher than that, but I'm talking about the incoming from the network, the provider. Very, very fast, and very little cross-channel interference there either. It's a version of the orthogonal frequency modulation that also incorporates that multiple input, multiple output channel bonding kind of thing. So now I don't use any of the channel bonding. I get plenty of speed with the blank setup that I have in my home network, but it's there. I mean, you can actually do that and set it up. All of these devices have a real slick management console that you can log into and manipulate all of these settings, set up the security, everything as far as managing the individual device. It still amuses me and amazes me in some situations. Finally, all of my neighbors, I can look at all the wireless signals that I have in close proximity to me here. And let's see what we have here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. I can see 11 other wireless signals from my home office here. And it's all the neighbors. One that's all around my cul-de-sac here. I see a couple of neighbors my back property line is the county line divider between my and the next county up north of us here. I can see 3 of my neighbors that are over there, all their Wi-Fi connections. For the longest time, I had 2 neighbors in my cul-de-sac and one in the cul-de-sac that's adjacent to us. They had no security at all set up on their Wi-Fi devices. And I've talked with a couple of them about it, told them about the issues and the possibilities there. And a couple of them went ahead, okay, well, yeah, come on over and show me how I can secure that. So I did. But I had one that was over in the cul-de-sac that's adjacent to us. He went for a couple of years and he just refused to even think about setting up security. I wasn't worried about it, and I was going, all right. And so I finally asked his wife. I got with the wife. I said, do you do banking or buy product? Or anything online, she's going, oh yeah, we do this and this and this and this and this. I said, all right, we got to tell old Jason here, it's time for you to secure your connectivity there. Somebody's going to take advantage of you. So we did. We finally got him on board and set it up there. The Wi-Fi 5 and Wi-Fi 6, very high speed connectivity that also utilizes versions of that multiple input, multiple output channel bonding thing. It also is utilizing the dynamic frequency selection. So it'll dynamically select a channel that is less noisy on any adjacent channels on other signals that's going on there. This right here is some of the fastest you're going to find. Wi-Fi 7. Now, and I'm guessing the Wi-Fi 7 components now are probably available commercially now. When they first published this version of this class, they were not. I think they are now. But screaming fast. I mean, screaming fast connectivity, screaming fast point-to-point connections in the wireless network itself. Very high quality capability of securing the connections from each individual endpoint to the wireless access point and back. The security built into these devices is there's one version of it, and it's called simultaneous authentication of equals, where the client computer itself authenticates to the WAP, the wireless access point, and then the WAP then communicates back and gives basically gives authentication back to the client. So they call it a four-way handshake or a dragonfly handshake, but it's the client and the server both validate to one another. Very, very tight bond. And it also uses some pretty heavy-duty encryption and what they call tunneling protocols, transport layer security, to very, very tightly secure the connection, the wireless connection. Because I showed you guys the product, the Wireshark product earlier for capturing data frames and packets that are flowing between endpoints in a network. You can use utilities just like that one and other utilities as well to capture wireless data frames right out of thin air. Okay. So you have to set up tight security on these things because, any what of the thieves, thugs, and malcontents I've mentioned can just drive up outside your home or your business, tap into your device. And let me share with you another little interesting component here. Let's go here. Nope, not that one. Let's go there. There we go. This website right here, and this may be disturbing to some, publishes every router password, user ID and password for every manufacturer and every model on the planet. Okay. Let's take a look at, I don't know. Let's look at the ASUS or Avaya. I don't know how many of those models they have. But it publishes, there you go, publishes all the user IDs and passwords. And that's the administrator's user IDs and passwords right there. If people don't go in and harden these things, change those default configurations, any of the bad guys can jump on those things. And if you don't have proper security set up, or if they happen to know the IP address of that device, which are also published, by the way, they can take full control of your device and have access to every device that is communicating with that wireless access point. So you definitely want to go in and change those administrative user IDs and passwords because they're out there for the world to see. Okay. The bad guys know where they are. The good guys should know that as well. This is an example of one of your management consoles, and this happens to be from a TP-Link router gateway box, box wireless access point. You go in here, you log in, you set up the security, you set up your passcode, you set up encryption. You can also set up inside here a listing of, much like the cam table that I talked about on the switch device, where you define individual systems and the MAC address that belongs to a particular port. You can do the same thing here and set up a MAC filter table. So only the systems that have the proper MAC address are allowed to log into your wireless access point. Okay. So there's quite a bit of security that you can do. You should become very familiar with the management console on your device. And even in your home network, you can call it up with a browser if you happen to know the IP address of that. And those IP addresses are also published. Actually, the standard IP address for your browser or your router inside your home network is probably 192.168.0.1 or 192.168.0.100. Okay, those are the two most often used IP addresses that are automatically assigned to your wireless access point. Okay. Now, there is another clever little tool. I'll give you guys a link to this as well. It's a tool that I have running on my mobile phone and on one of my Android tablet devices, and it's called a Wi-Fi analyzer. The name of the company is, I believe it's CoolSoft. Yep, there we go. No, not Keysoft, CoolSoft. Right? Maybe it's UL. Nope, still not finding it. All right, let's try this. There's Google's. There is, I'll find this site here. It is a free tool. All right, you're gonna make me get down and dirty, I see. There it is right there, KEUWL. This is a great little tool here. It is free, and it allows me to do basically a walkabout in my wireless environment here. And I can see all of the wireless access points that are available in my general vicinity. Now, if I go back to that, I'll show you a couple of cool little features of it. It shows me on the screen, basically gives me a listing of the SSID name, the strength of the signal, the channel it's broadcasting on, give me all of these overlapping signals, the Wi-Fi, a basic service set identifiers of these guys, channels are broadcasting on, signal strength, all of that. And it is a free application. Now, it does not run on iOS. So you have to have an Android device, Android phone, Android tablet. But it is a free tool. And the cool thing about it is it allows me to walk around inside my environment and see things such as broadcast channels, SSID names, signal strength, any overlapping channels. And I basically paint what's referred to in the networking world as a heat map. So I can see areas where I might be getting interference into signals, where a wireless access point may be overlapping another. Okay. So that allows me to actually position and arrange all of the appliances inside of my network environment so that I am broadcasting a good, powerful signal, but only to the users that it should be servicing and not overlapping others. And if I'm getting interference from some other areas like microwave ovens or overhead power lines or that alien crosstalk interference from power cables that are too close to my Wi-Fi access point, those kind of things. So the Wi-Fi analyzer is a great little tool to assist me in doing that kind of evaluation of my network environment in general. Okay. Now, when I'm doing a wireless setup, like a wireless wide area network LAN or a wireless LAN, had the opportunity to work with the networking folks. This was years ago up at the University of Wisconsin, in Madison, Wisconsin. And I worked with their engineering folks up there, and we did some consulting and helped them set up their own campus wireless network. Now, and the beautiful campus up there, by the way, if you guys ever get the opportunity, you should visit. But beautiful architecture, beautiful buildings, spread out pretty good. So we had to put these dipole antenna that was broadcasting the wireless signal from building to building to building in and around the campus there. And there's several different types. There's small dipole antenna, a little dish about I don't know, about 11, 12 inches with a dipole antenna in the middle. And it has to be, it's point-to-point line of sight kind of connectivity. But there are other antenna too that are omnidirectional kinds of antenna. We see those that are used especially inside buildings where if you're wanting to cover a large common area with a wireless connection, they'll use the Omni 360-degree antenna broadcast there. If you're going over long distances, according to the power requirements to get a signal from one location to the other, you may have to get into a licensing situation on those. Now, in most close proximity wireless LANs, you're not worried about getting licensed to broadcast a signal because you're just not broadcasting with enough power to interrupt any other type of radio frequency signals in the area. Okay. Now, another type of, we talked about the personal area network, the PAN. Most of your mobile appliances, your mobile phone, your headphones, I got a cool little set of earbuds here that I've been playing with that are specifically matched up to my particular phone. I like them a lot. If I hook these earbuds up to my mobile phone, that's a personal area network. If I hook my mobile phone up to the little bullet type speakers I have here, that's a personal area network. And it communicates Bluetooth. Bluetooth is also a wireless type of communication mode that also uses 2.4 gigahertz frequency ranges. It's relatively close proximity, usually no more than about 10 meters, 28 and a half feet or some odd. Now, there are other stronger Bluetooth signals I can use, but it's the same thing with my wireless mouse and my wireless keyboard. They actually communicate with a USB dongle that plugs into one of my USB ports, but they communicate Bluetooth from this device to the dongle. Same thing with my keyboard. It's wireless. It has another little USB dongle that plugs into one of the ports, and it communicates Bluetooth. My computer system is set up to do Bluetooth direct printing to my printer. And it actually can do either direct Bluetooth printing or Wi-Fi direct printing wirelessly. So, and those are all different flavors and versions of localized personal area network frequencies there. Now, we also have seen, and I guess Walmart was one of the first retailers locally anyway, that started using these RFID chips, radio frequency identifier chips. And that's where they put the little RFID chips on, on product, and then the sensors that are at the entry and exit doors that go off if somebody didn't purchase the product, that kind of thing. There's also, and we've seen too, now I don't know if you guys remember this, several years, the first time I ever realized what this was all about, several years ago, there was a TV commercial that I saw, and it was a couple that obviously was standing on the premise of the Grand Canyon, and the fellow was taking pictures, and the girl says, "Oh, well, email me those pictures." He says, "No, let me show you." So he takes her phone, his phone, just tapped them together, and it transferred those images to her phone. We've seen the same thing with transferring bits of contact information. Just touch the phone. It's called near field communications, NFC. And then that has now evolved to your tap to pay kind of contactless payment type of stuff. And even things like, auto entry badge information, transmitting entry badge information to electronic locks, things like that. Now, NFC is very close proximity, whereas Bluetooth is somewhere in the neighborhood of about 10 meters. Radio frequency IDs is about 28 to 36 inches is as far as you get on that. NFC is very close, about 9-10 centimeters. So, it's all according to the strength of the frequency or the strength of the signal and the frequency it's broadcasting on. Bluetooth is now being utilized to communicate with just about everything you could imagine in a wireless mode. Like I say, my mouse, my keyboard, the phone, the speakers, the headsets, the earbuds, all of that is pretty typical. And of course, all of these portable appliances have Bluetooth baked right into the appliance itself. So very, very common for those personal area network connections there, and even now incorporated as far as the local area networking by doing things like that, Bluetooth printing or Wi-Fi direct printing, those kind of things. So it all incorporates multiple types of wireless connectivity. Okay. So remember the IEEE specifications. Remember the IEEE.A specs, or IEEE 802.11 specs are for wireless networks. Remember 802.3 specs are for wired networks. Remember the configurations of those, the twisted pair cabling, the color coding. Remember the three different types of ends that we talked about, the straight through cable, the crossover cable, and the rollover cable. Those are the things that you're going to get asked about on your certification exam. Okay, no doubt about it. Now, for you folks that are tuned in on YouTube or that are joining us as audit students, what we're about to do now is the students will be taking a module quiz. At the end of each one of these modules, we take a module quiz, and so, it's anywhere between 10, sometimes 15, 20 questions. This one is 20 questions total. What I usually do is set up a timer on these, which usually gives them about a minute per question. I'll do the same thing here, set up a 20-minute timer. And well, I'll tell you what, I'm going to go ahead and do a 30-minute timer now because, well, yeah, we'll do a 30-minute timer here. That will give all the students here time to do this module quiz, to post the scores, and to go ahead and take a quick latrine break here. Okay. So any questions at all before I set up your timer and pull the trigger on this? Now, of course, you folks out on YouTube and you folks that are auditing will not be able to take this module quiz, but you are more than welcome to hang with us while this is going on, and we'll be picking it right back up in 30 minutes. Okay. Also, the students post their scores online, and that is more for their reference than anything else. And I always encourage them. There's no shame in the scoring at all. What the scoring tells you at this point in time is you know what you know, and you know what you need to work on as well. So once again, any questions at all before I go ahead and set and pull the trigger on this timer? All right, dive in those quizzes, folks. Enjoy yourself. I look forward to seeing the scores there, and then we'll dive back in here after this is over and have some more fun with some more lecture here. So you guys hang with us. We'll be back shortly. All right, folks, welcome back here. Let's get ready to re-engage once again. Okay. Now, this next session here, we're going to go till somewhere in the neighborhood of 1:45 to 2 p.m. Eastern Standard Time. So then we'll be taking our lunch break at that time. And for you folks that are tuned in on YouTube, we'll be stopping the broadcast at 2 p.m. Eastern Standard Time. And I see we have yet another audit student has joined the party here. Kaylee J. It looks like. Kaylee, welcome to the party here. I welcome you to the class, and I want to encourage you to participate if you wish. I always have my audit students primed. If you have questions you want to ask while we're going through the session here, you feel free to do so. Jump in and open your mic, ask the question, raise the hand, type it into the chat box. Either way, I will try my best to address it for you. Now, this particular session here is going to look specifically into network setups, network configurations, internet connectivity, even into your addressing. Now, we talked earlier about the physical address of your computer systems. The MAC address is associated physically with your network adapter. It never changes. It is a permanent physical address. That's the hexadecimal address that we looked at earlier in the day. Now, in order to communicate out over an IP network, an internet protocol network, the address that's used there is your IP address, not your physical MAC address. And that's for, a couple of reasons behind that. They don't want your physical address being exposed out over the public internet. I want to keep that private. But it is the delivery vehicle that is the last step, if you will, to get a frame or a data frame or a packet delivered to your particular computer system. Okay. So we're going to take a look at some of your internet connectivity types. We'll take a look at some more terminology now that you need to be aware of as far as the infrastructure of the internet in general. Now, when the 3 or 4 different think tanks began to put together the framework and the infrastructure that would eventually become what we know today as the internet, they realized pretty quickly and began to build upon the foundation that was already laid by the telephone companies, the telcos they call them. All over the country back then or in the United States anyway, and in some areas in North America as well, in Canada, there were these what they call baby bells. You had little hometown, personally owned, privately owned telephone companies that were everywhere. You couldn't go to any little hometown location, hills and dales. If somebody needed telephone connectivity, they say, "Oh yeah, the block building over there down on 3rd in Main, that's the telephone company." And sure enough, that's where you went to get your physical hookup of the wire to run out to your home or your business, wherever you needed the connectivity. Well, throughout the years, then these large conglomerates like AT&T and Sprint and Verizon and Comcast and the list goes on and on, these large conglomerate telecommunications organizations begin to go and buy up these individual baby bells, they called. And that's what we now have, for the most part, 3 or 4 major telecommunications carriers, again, in North America, a handful, 5, 6 perhaps, it includes Canadian telcos, that have consolidated all of not only the businesses, but the infrastructure, the wiring that is in the ground, the wireless towers that are set up hither and yon, that incorporate now what are referred to as ISPs, Internet Service Providers. Now, all over the planet, there are these massive, massive size data centers and they're called IXPs, Internet Exchange Points. I got to visit one a couple of years back. Young man that used to work for one of my companies is now one of their head engineers. And I can't tell you what the location is for security purposes and because I'm bound by non-disclosure, but I can tell you it's one of the most massive sites I've ever seen in my life. Literally hundreds of thousands and probably even millions of wires of every form and fashion you could imagine terminate in this large internet exchange point. That's where all of the telephone wires, the copper cabling, fiber optic cabling, leased lines, you name it, they all terminate in this massive, massive tunnel, in essence, data center. Deep underground, as a matter of fact. And then all of your local internet service providers have their equipment, their cages, and their server routing, switching equipment all housed inside this large, massive data center. And they hook into all of those terminated wires. Okay. So the wires and infrastructure that is the framework of the internet terminates in these things. All the ISPs put their equipment, and then they sell that internet service connectivity to we the customer out in the field here. Okay. That is the basis and the infrastructure of the World Wide Web. That's what allows you and I to be able to tap in through our browser, through our home connection, and communicate with any other user in anywhere else in the world is by way of that multi-point infrastructure. Okay. That is indeed the fabric of the internet. Okay. That fabric terminates in our location, much like we looked at here earlier. Okay. Your Soho or your home office or your home, your domicile, you have this box here. This is your router, gateway, switch to box now. The modem is incorporated in here as well. You have all these individual points here on this globe down here. Those are the IXPs, the Internet Exchange Points. And then within those, you have your ISP that has their equipment located in there. And the ISP, the Internet Service Provider, they then incorporate and connect to what we call our demarcation point, the demarc, which is in essence the handoff I talked about earlier from the internet service provider to your home or your business. Okay. Everything on the inside of this demarc is your responsibility. Everything on the outside of this demarc is the responsibility of the internet service provider. Okay. And regardless of the configuration internal in the network, okay, it doesn't really matter. Regardless of that config, it's your responsibility on this side of the demarc, and everything on the outside, responsibility of the service provider, you see. Now, inside of your network, you will maintain typically what's called a private IP address schema here. You will have typically set up what's called a DHCP, a Dynamic Host Configuration Protocol server. And you will decide usually between what's referred to as a Class A, a Class B, and a Class C range of internet available addresses. Now, first, I want you to understand something about the way the IP addresses were originally formed. I told you before that when the internet first came to be, the computer systems at that time were based on a 32-bit operating system and a 32-bit data path on the motherboards. Okay. So the powers that be, the think tank says, well, we need to have a 32-bit address that we assign to each of these individual computer systems here. So they came up with this Class A, Class B, and Class C range of network internet protocol addresses. And they the way that we human critters look at it is much like this noted here. Okay. 192.168.0.1, 192.168.5.102, or whatever. Each of those separation points here on this network addressing is referred to as an octet. Okay. This guy right here is an octet. They call it an octet because the binary to decimal equivalent here is 8 binary bits for each of these sections. Okay. And then you do a binary to decimal translation to derive the actual decimal version of this address that we human critters know. Now, 32 binary bits, if you look at that as far as the possible addresses that can generate, it actually is a value of something it's about 340 billion available addresses within that range. And that's, if all the binary bits are 0, that's all zeros, or if they're all turned on, that's all ones. So if you do the decimal translation, that is from 0 all the way up to 255 for each of these octets. Now I'm going to show you how we actually translate those from binary to decimal here in just a little while. So hang with me on that. But because we human critters aren't particularly fond of trying to evaluate binary data, ones and zeros, this long string of 32 ones and zeros, that's where we do the binary to decimal translation. Now, when the IETF, which is an organization, the Internet Engineering Task Force, there's another group called ICANN, the Incorporation for Computer Assigned Names and Numbers. When they decided on this addressability, they determined that of all of that somewhat 340 billion some odd available addresses, they almost cut it in half and said, well, the range of these addresses we're going to allocate to be what's called private addresses. They'll not be used to transmit out over the public internet. They'll only be used inside of the constraints of an autonomous network. Okay. So they allocated those. There's actually 5 different classes that they allocated of those. The ones that we use for our own use inside of private networks are called class A, B, and C. More on that later as well. And then the remaining data or ranges of internet addresses, they called public IP addresses. This organization known as ICANN, and there's another organization called IANA, Internet Assigned Names and Addresses. They actually perform a function called leasing, where they will assign or lease one of these public IP addresses to a private company or to a publicly owned company. So that is the address that is utilized for all the traffic that flows from the company out over the public internet. Okay. So anything going outbound is all a singular IP address in most cases. Now, larger companies, larger enterprises, they may have 2, 3, and even sometime a pool of 20, 30, multiple IP addresses that are leased to them. So all the traffic that goes out over the public internet from those companies is from those public IP addresses. All the traffic that's moved around inside of the network, that movement occurs either based upon the MAC address or the internal private IP addresses that are assigned to each individual host machine. Now, there is another acronym, and you need to be aware of what this is. We'll touch more on this later as well. But the acronym is called ARP, A-R-P. That is Address Resolution Protocol, ARP. You'll hear the term ARP cache. When I log into a network session inside of a network, what happens is my computer presents my MAC address to the closest DHCP server and says, I'm ready to log into an internal session. Here's my MAC address. I need an IP address to go with that for the duration of my session. So the DHCP server goes and looks at its pool of available IP addresses, picks the next one off the stack and assigns it to my MAC address. And it updates that ARP cache and says, all right, for the duration of this session, your MAC address is going to be associated with this particular IP address. it removes that IP address from the pool so that it doesn't assign that duplicate address to anybody else. Okay. So for as long as I'm logged into that session, as long as I am active, then that IP address and my MAC address are joined at the hip, and that information is reflected in the ARP cache, the address resolution protocol. Okay, so my physical address and my logical address are matched up the whole time I'm logged in. Okay, so remember that acronym. Remember the difference between private IP addresses and public IP addresses. And again, more detail on that to come here. Okay. So next thing down the line here is the way that the networks are actually created originally anyway, was with the existing telephone telco infrastructure. All the wires that were hanging along telephone poles, along railroad tracks, that were buried into the ground, all of that existing framework, that copper wiring originally, was what was referred to as the public service or the public switch telephone network. Now, old telco guys call those POTS lines, POTS, plain old telephone service. Okay, so and originally the telephone wires, I don't know if you guys remember this or not, but the telephone wires are only 2 wires. Okay, 2 copper wires running down that little flat, and saying originally it was just the round wire. Then they upgraded it to 4 wires when people started wanting to have 2 telephone lines in their home or their business, that kind of thing. Okay. So that was that copper. It wasn't twisted pair cabling, just straight run copper cabling there. And originally as well, I was mentioning you the story yesterday about Miss Erlene. The power for the analog telephone wires, it didn't rely on plugging a telephone into a wall socket. It used DC direct current that was sent right down a couple of those extra wires. And that direct current was what allowed things like the telephone handset to ring. Okay. So even if the power in the home was out, if the direct current from the telephone company still had power, you could still get phone calls. Okay. So, and yep, I'm older than dirt. I remember way back in the dark ages when all this stuff was true. So the first entry into the internet world was by way of this modem. It's called DSL modem, a digital subscriber line. And the very first flavor of that used to use these splitter boxes, these DSL splitters, where you would have the phone line, the regular old 2 or 4 wire phone line would plug into one of the plugs in this guy. You would then hook up your internal home telephone service to the other plug, the telephone plug, and you would have an Ethernet cable, an 8-wire twisted pair cable that hooked up from the ADSL box to the modem, to the modulator demodulator, another piece of equipment. Okay. And then they started incorporating the modem and the wireless access point into a singular box, but it also would plug into this ADSL splitter. Okay. Now, the asynchronous or asymmetric digital subscriber line, very slow. They always promised that you could get somewhere in the neighborhood of 26 to 30 megabits download. You never got it. You might get 12, 15. And the upload speed was even slower. They would promise that you could get somewhere between 10 and 12 megabits per second upload. You never got more than 3 to 6. Okay. Just the nature of the beast. We had another version of DSL, which was called symmetric DSL, and it gave you the same upload and download speeds, but you had to be closer to what was called the POP, the point of presence, okay, the telco in essence. And the speeds, they never were able to get what they promised ever. And then there was another version of it, was called VDSL, very high speed digital subscriber line. And they promised anyway, 50 megabits and sometimes 100 megabits per second. Of course, we're never able to deliver it. And in order to get that connectivity, you just about had to be able to throw a rock out your window and bounce it off the wall of the telco, of the POP, the point of presence. Okay. So, but still in all, for the times, Being able to hook up and get that connectivity was the cream of the crop there. Okay. Then we started seeing the introduction of these cable modems. That was the cable box and the modem all baked into one. It utilized this operating system called DOCSIS, and it's direct something cable service. I don't remember what the acronym is, but that was the operating system that they used in most of the cable modems. The cable modem would use either the F-type connector, or some of them use the B and C type connector, push and connects, but most of them use the F-type screw-on connector. That was the incoming signal, the high-speed internet signal coming into your home, and then you had the Ethernet connections outbound on that, usually to a wireless access point, and then they communicated, your devices inside your home communicated wirelessly on that as well. But that's when we first started getting the combination of cable TV and cable internet access combined into one. That's one of the things that the DOCSIS operating system provided for us. Okay. So that was the cable modem. That was the next iteration. Then we started getting fiber. Now, in most, especially large metropolitan areas, we have fiber to the premises, they call it, fiber to the home. Full fiber, and mine here does, and our little cabin up in the foothills, comes through the wall, fiber optic cable plugs right back into the back of the wireless access point, router, modem, gateway device. Some of them are still, and I've seen especially in some suburban areas where they have what's called fiber to the curb. It's sort of a hybrid combination. They run the fiber to like a little box that's at the cul-de-sac or at the end of the street, fiber to that, but then coax cable into the individual home. So it's sort of a hybrid. Fiber optic cabling now is certainly the way that the internet is evolving, and they're trying to, even giving government support monies here to try to give high-speed internet access to all over the country. Hadn't gotten there yet, and unfortunately there's a lot of tricks going on underneath the covers with politicians on that stuff, and money's disappearing, and we've all heard the reports on that. But the full fiber optic to the home, to the premises, or to the business is what we're shooting for. Now the modem access point boxes themselves are multifunctional, like the one I was telling you about I have in my home here. Doesn't have the antenna exposed on the outside anymore. The last one I had 4 antenna. Now the one that I have up at the cabin still has 4 antenna. It's a different box, and it uses a fiber optics right into the back of the box. But the antenna are flexible. They call them rubber ducky antenna, but they're positional. I can point them in certain directions. And it is also one that gives me all 3 of the frequency bands, 2.4, 5, and 6 gigahertz. The one I have here it's a brand spanking new one I purchased, and it doesn't have any exposed antenna, but it also gives me the full function of the 2.4, 5, and 6 gigahertz frequency bands there. We are also beginning to see, and a lot of this is experimental on these, they call it WiMAX networks, or WISP, wireless internet service providers. There was a company that came here, and this has been a couple of years ago now, and they were an abject failure. We live at the foot of they call it a mountain. It's actually a little foothill here where our home is. And up on the top of the mountain, this company came in, put up a tower, and they had several of the direct dish antenna that they were trying to focus the WiMAX networks, or the WISP networks. And we were one of the beta customers for them for a while. And we got a little unit that we just plugged in. I had 2 of them here in my home, plugged into an electrical plug in the home. And the concept was that it was using the existing electrical wiring in the home as the antenna to receive the WISP signal. And it was one of those things to where when it was working, it was awesome, but it hardly ever worked. And I think they managed themselves out of business, because it wasn't long. Some of the company reps says, well, yeah, the company's not going to be able to launch this service. And please, they gave us a mail and some UPS tickets to mail their equipment back. So we did. We're also seeing quite a bit now, and Elon Musk and his organization is one of the first in this arena with these LEO satellite grids, satellite networks, low Earth orbit satellite grids. I know people that are using the SpaceLink satellite grid, the LEO grid. It is awesome. I taught a class at a military base up in it's actually borders on between Tennessee and Kentucky. It's an area where they do the technology updates on the Black Hawk and Apache copters. Pretty highly secure environment. They wouldn't allow us to use internet, just public internet access, wired access anyway, inbound into their environment. But the sergeant major, who was my liaison, brought in his SpaceLink kit, and we just set the antenna right up on top of the hangar building there, and gave us the wireless, very secure LEO satellite internet access we needed. I had like 28 people in the class, and it was screaming fast, unbelievable, up all the time, every time. And the LEO satellites are quite different than the old satellite TV networks we used to have. You guys, if any of you guys ever had satellite TV, you'll remember. I mean, geez, flock of birds fly over, or the wind blows too hard, you lose the signal. But the new LEO, the low Earth orbit, not only are they considerably closer to terra firma, the TV satellite networks are like 23,000 miles up, geostationary orbit. The LEO satellite grids, they're somewhere in the neighborhood of 450 to 600 miles up. And I noticed that the SpaceLink they've actually adjusted, and they're even in a lower orbit than they used to be. And it's for safety purposes, other satellites that are up there as well. But the way those things works is you get your signal simultaneously from typically multiple satellite feeds, rather than having to be tuned in directly to a singular transponder on the old satellites. Plus the distance is, radically, I mean, it's a third of the distance physically as the old network. So you don't have the latency problems that they had in the others as well. Now, in addition, some of the older generations of cellular technologies, 2G, 3G, and 4G, not 4G LTE, which is a long-term evolution. 4G LTE and 5G are pretty much taking over all of the cellular traffic business all over the planet. And we've pretty much evolved now, even though especially some of the 4G LTE, the long-term evolution networks, are still supporting the old means of the networking, which was called CDMA, division multiplex access or something like that. It didn't use, I mean, even though the phone sets usually had them, but they didn't use the SIM card to track the user and the phone module itself. It used a couple of databases, tables that were moved from tower to tower to tower as you were moving through the network, the CDMA version. Now, all of them beyond LTE are what they call the global or the world phones, the GSM. And those do indeed use the SIM card, the subscriber information management card there. So it tracks not only the owner of the service, but the device itself with the SIM. And it's either a physical SIM or an eSIM I've used on my new phone here. And then the 5G networks, the 5th generation cellular, screaming fast. It has the same built-in multiple input, multiple output function, only the mobile version of it now. Very fast, very strong signal, unbelievable frequency bandwidth available, but the same as the 5 gigahertz Wi-Fi signal, the 5th generation cellular signal doesn't propagate well through solids. And it's many of the same frequencies that are used in the 5 gigahertz Wi-Fi range. But it's not the same thing. It's two separate modulation techniques, everything. But so we're seeing lots of these 5G antennas springing up everywhere. so that they can propagate those signals, especially in convoluted, metropolitan areas, things like that. And you guys have probably seen them, especially in large cities. They have these large columnar-looking tower things that usually on the same street corners with the traffic lights and stuff like that. And out in the wild, I saw a bunch of them. I was teaching classes over in Oahu, DoD classes as well, and all out in the wild driving around the island, they had these. It looked like pancake stacks, is what it looked like up on these towers out in the middle of nowhere, and those were the 5G antenna that they're using to really push and propagate those signals. We're seeing some of the older generations of cellular, 3G, 2G, and the base level 4G are sort of being repurposed into other areas here, agriculture, logistics, transportation, things like that, as far as tracking computer-based components there as well. Now the router box is one that makes a couple of very important decisions when we're moving traffic. The router evaluates your IP address. The router is, if you look at the network model, there's a layer in the network model called layer 3. It's a network layer. It is associated with the physical router component itself. Extremely intelligent boxes. These things dynamically communicate with other routers inside of a network as well as outside other autonomous networks as well. The routers give us the ability to sub-segment or to break down a larger network into smaller sub-segments or sub-components. We do that by the router making decisions such as, am I trying to communicate internally, with other users in the same segment, or do I need to route this to another router and then deliver that traffic to a different local area network? Okay. So it makes some pretty intelligent decisions, and it does it blindingly fast. There are, three major types of routing protocols that we see used. And when I'm talking about protocols, that's just software. A protocol is implemented by some application, some software protocol application. The IP address takes a request from one computer system, and the router says, well, are you and the computer you're trying to talk to in the same network or network segment? Yes, you are. Well, it then probably would throw it back to the switch and say, handle this MAC address to MAC address. We don't really need the IP address for that. Okay. Or if it evaluates your IP address and the IP address of the target you're trying to send to, and it recognizes that you're in different network, well, then the router picks that up and then finds the closest router that can service that particular network or can move that packet on to the next hop where it can be delivered to the network that you're wanting to deliver to, or where that user happens to be. Routers, like I say, an extremely intelligent device. They make these picosecond decisions. And another thing that they do quite well is they recognize other routers. They broadcast what they think is the best route from one location to another location in a network to all of these routers. And the goal of these routers that are soliciting their routing tables and reading the other routing tables of all the other routers, the goal is a concept called convergence. And the convergence term means that of all the routers that we have in this autonomous network, they have all pretty much come to an agreement that from this host computer to this host computer, this is the best route you need to take. From this host computer to this host computer, this is the best route you need to take. Okay. And the routers make those decisions dynamically. Okay. Very intelligent boxes. We're also beginning to see, and I mentioned this earlier when we were talking about the switches, the functionality of the router, the switch, the gateway, even the firewall is all being aggregated into these singular, very powerful new boxes. Now, we'll talk more about routers and IP addressing and that later on here. Firewalls, proxy servers, even routers, gateway appliances. They typically make decisions as to whether to allow a data packet into or out of, that wall based upon what's called an ACE. An ACE is an access control entry. You'll oftentimes hear it referred to as a filter. If I set up multiple ACEs in a listing, they call it an ACL, access control list. So, and those are just rules, things that I evaluate the data frame. And if I hit on a rule that is satisfied, well, it either allows it or denies it. Okay. But it will go top to bottom down the list. And they call the way that firewalls operate by nature whitelisting or implicit deny. Okay. So I have this set of rules or ACEs, a set listing of access control list. A data frame is introduced into the incoming port of the firewall. The firewall says, okay, evaluate it, either allow this or allow this or allow this or allow this, but deny everything else. So unless I explicitly allow a data frame, if it's from an IP address or a MAC address or a domain, unless I explicitly allow those to pass through with a rule, they're implicitly denied. But I can evaluate those based upon, again, an IP address, the port number they're trying to communicate on, the protocol that they're trying to communicate with, the IP address, the MAC address. There's so many different things I can set up to filter out unwanted information. Okay. So, but I have to be very cautious in the way that I set up my filtering entries. And remember, unless I explicitly allow something, the nature of the beast is to implicitly deny it. Okay. And always in my firewall rules, when I set those up, the very last filter is deny all. So allow this or allow this or allow this or allow this, but deny everything else. Okay. And firewalls are more often than not nowadays, they are software driven. It's an application running. Some of the very first hardware based firewalls way back in the day, you even had to do plug wiring on those things, much like the old telephone operators, that kind of thing. It's pretty interesting the way that we used to have to program the rules into a firewall device. But now, like I say, it's pretty much come down to software driven firewalls now. And for the most part, we're seeing the firewall functionality is beginning to be aggregated into the router gateway, box as a software component inside that. Okay. So the different types of modems that we looked at, a couple of those of different types of configurations there, wired and wireless. That's the kind of things that you're going to be tasked with. And I'll tell you guys, I told you this earlier. You might as well go ahead and get used to the fact that when you get these certifications under your belt, you are immediately going to be assumed to be the expert, including being an expert in networking. Okay. Unfortunately, that's the nature of the beast. So, in lots of companies, you're going to be wearing multiple hats. So this is just the beginning of your journey on the education realm here, no doubt. Now, I talked about the network stack. There's actually two major, what we call network models. We are beginning to see that many networking organizations are moving away from an older model. It's called OSI, operational model. It had 7 layers, and moving to this, what they call the TCP/IP model. Now, this actually is also referred to as the DoD networking model as well, 4-layer. You have the bottom layers there. Sloan is saying access with the learning platform. I haven't checked mine in a while, Sloan. Let me see if I'm doing okay. Hopefully they're not doing any updates or things like
I'm
that.
also unable to get in. Yeah, I have that same
Yeah,
error.
same thing with me. I'm getting the network error there. Huh,
I'm
that's
getting, yep,
interesting.
it's the same thing here. I was just sending you a message over the chat line.
Okay. Yeah. Um, hmm. I'll put a message out to Mr. Stalling and have him troubleshoot that. So that's systematic on their end for sure. It's not just all of our connections. Okay. So, but we'll get it back up. The network model here, the bottom layer here is it actually incorporates the bottom three layers of the old OSI network model. It's the physical layer, the data link layer, and the network interface layer here, all incorporated into this link layer here in the new model. That's where we have things such as your network adapter, your MAC address, okay, the switches, bridges, hub devices, even wireless access points, all are associated with that very first, that physical link layer, they call it in the TCP or the DoD model. Notice huddling between this layer and the next layer up, which is called the internet layer, is the ARP cache I talked about earlier, because it makes that connectivity between your physical MAC address, which is on your network adapter, as we see here, and the logical IP address that is assigned to allow you to cruise the internet or to go through IP networks as well. So the ARP cache sort of sits between those two. Next layer up, pretty important here, called the transport layer. The transport layer performs one major and a couple of other minor functions here. Every communication session that you want to make with a target system utilizes some type of communication port and software protocol. Now, you'll need to learn these common ports, and one of the documents I gave you guys to download off of that wormhole site was a common ports document. For instance, if I want to send an FTP file, well, the communication port on the target system I want to talk to is port 21. That's FTP, port 21. If I want to fire up a session with a web server, fire my browser up and connect to a web server, that is either the HTTP protocol, which is non-secured, which is port 80, or the HTTPS protocol, which is the secured. And HTTP is Hypertext Transport Protocol, by the way. The Hypertext Transport Protocol secure uses port 443. It's called a secure socket. On every computer system, there are 65,534 logical communication ports. Okay. And then different software protocols operate by default over some of those specific ports. Again, HTTP port 80, HTTPS port 443, FTP port 21, Telnet, which is just a command line connection to a target system, as port 23. And then all of your other software protocols, your domain name services, as port 53, your DHCP, Dynamic Host Configuration Protocol, port 161. Your directory services, LDAP, they call it, Lightweight Directory Access Protocol, port 389. And so the list goes on of the common software protocols that you want to talk with and their default communication ports. Okay. Well, it's going to be important for you to know those ports. They'll show you a chart here in just a little while, and those are the ones you need to concentrate on. What the transport layer does is makes the determination based upon your communication port you're trying to talk to. It associates that with its target communication port and software protocol. And it also makes another very important decision. Some of your communication protocols operate in what's called TCP or Transmission Control Protocol mode. Some of them operate in what's called UDP, User Datagram Protocol. Here's the difference. TCP protocols are connection-based. You establish a connection to that target system. It acknowledges that connection. You do the handshake, and now you're bound to that communication target. It's timed, it's synchronized. back and forth, acknowledgement, acknowledgement, acknowledgement. Okay. It guarantees not just the integrity of the data, but the delivery of the data. Now, people tend to think that data that's traveling over an IP network is just one constant stream. Not at all. The system breaks that up into what we call data frames or data packets, short segments of that data. And it sends it across these IP networks. Well, each of those frames or those data packets has a sequence number assigned to it, so that when all the packets are received on the other end, it reorders those, because they may have gone very different paths through an IP network. Because, you know, it may have been sending data frames through one channel, through this router, this router, this router, and this router to get to the target location. And all of a sudden, one of those routers fails. So the router before it decides to send a different path. So the data frames may be received out of sequence. Okay. If it is a TCP connection-based transmission, if one of the data frames drops off the network or is damaged, the target system will continually send back to the sending system, hey, I didn't receive sequence number 1534, resend it. And it will wait until all of the data is received, and then it assembles the data stream and then plays it back to whatever application you're talking to on the other end. Transmission control protocol, connection-based. User datagram protocol, on the other hand, it's what's called best effort. Okay. There's no timing, there's no established session, there's no synchronization, none of that. Now, the data frames are still have sequence numbers, but if a sequence number is dropped, well, you don't get replayed. You guys experienced this, or Sloan did earlier, when you were talking about that I either froze up. Okay. Well, it didn't resend those data frames. It was just oh, well, you know, the sequence was dropped or damaged on your end. Okay. So that's the user datagram or best effort transmission. Some of the communication protocols only operate as TCP. Some of the protocols only operate as user datagram protocols. And some of them will make that decision at communication time. So it evaluates a whole host of metrics, things such as, well, is it a good solid data path? Do I have bottlenecks? Do I have large degree of drop frames? So we're going to do user datagram instead of TCP. But there are some of those that only operate in one or the other. Either way, the transport layer in the network model is what makes that decision real time, based on what you're trying to talk to, how you're trying to communicate, that kind of thing. Okay. So, and then at the very top layer of the network model here, the application layer, that's where all your applications, your simple network management protocol, all of your email protocols. There's 3 email protocols: simple mail transport protocol, post office protocol, internet message access protocol, IMAP. IMAP 4 is the latest version of that. Your dynamic host configuration protocol, DHCP, DNS, domain name services. And I talked about FTP and HTTP. You got server message block. You got network time protocol. And there's a whole listing of different software protocols, and each and every one of those has a very specific default communication port associated with it. Transport layer is what makes that determination and sends it to the appropriate communication port on the target system for that particular software protocol. Okay. So that's basically the TCP/IP network model. Okay. Now, if I am operating locally, okay, if I'm hooked up, you know, me and all you guys are hooked up to the same physical switch, we may or may not be associated with the same subnet or network address. The router box usually makes that determination. Okay. So if I'm just wanting to communicate with somebody on the same switch in my same network segment, it's just MAC address port to port communications there. If I'm wanting to communicate with somebody in a different network or a different subnet, The router makes that decision, and it's based upon what they call the PDU frame in two very, very particular fields. PDU is Protocol Data Unit, is what that acronym is. Inside that first frame there is the source address and the target address that I'm trying to send to. And that is either a MAC address or a IP address addresses there in that PDU. Okay. So as my data frame traverses up from the link layer, that's where it uses the MAC address for, system-to-system communication or forwarding from one port to another port. If it goes up through hands off to the internet later, then that MAC address is translated to whatever IP address. And remember, the ARP cache that huddles between those two makes that transition there. Okay. And then it moves on up to the transport layer. The transport layer says, all right, you're trying to communicate with this particular software and port number. So I look in my table and say, well, that's a TCP only communication protocol. So we're going to have to establish a connection, wait for the target system to acknowledge that establishment or request, and then we send back the third leg or the handshake on that. Now we're bound. Now we start exchanging data frames. Or if it is a user datagram protocol only, UDP, then it's best effort. I don't have to ask to transmit or anything like that. This video is a UDP type of protocol. Okay. I just start blowing the video down the pipe and you can jump in on it anytime you wish. And like we were experiencing earlier, if a frame is dropped, oh, well, it's dropped. If the video ceases, when it comes back online, you just pick up where we're going real time now. You see. And the transport layer is what makes the decision on which one of those it's going to be. And then the application layer is what you're actually talking to on the other end. FTP or a web page or an email client or server. It's all according to the protocol you're using. Okay. Now, here's where it gets fun. I want you guys to break out your calculator right quick while I'm putting together something here right quick. Okay. Oh, let's get off that and go over here and do that. Okay. Now, a couple of things I want you to be aware of here. When we're doing binary to decimal translation, remember I told you first, we broke down that 32-bit binary address to 4 octets, okay? 4 sets of 8 binary bits. In order to translate those binary data to what we humans know as decimal data, we have to use, in this case, because binary is a base 2 numeric system. It only has 2 values, 0 and 1. So what we do is assign what we call placeholder values to each of those 8 slots in that octet. And those are powers of 2. You'll see what I'm talking about here in just a sec. These are constants. They never, ever change, and you'll see why. Okay. 8 binary bits there. If I start on the right-hand side, all numeric systems begin with a value of 1. Some people say they begin with 0. 0 is not a real number, so we don't use that in our calculations. If you go then from here to the left, okay, these are powers of 2. Start with 1, 2 to the first power is 2, 2 to the second power is 4, 8, 16, all the way up to 128. These are placeholder numeric values. They do not change, okay? Now, here is the way we actually calculate binary to decimal. Now, what we're going to do is take this binary bit collection here, And we're going to associate each of these individual binary bits with all of these placeholders. So it will be 1, okay, 1, and then all zeros. Now, with your calculator, everywhere there is a value of a 1, right here and right here, you add those placeholder values together. Okay. And if you're quick on the draw with your calculator, you should have come up with 192. Okay. Now, let's do the same thing with this. You guys are going to do it on your own, however. I want you to align these binary bits with each of the placeholders. Everywhere you have a value of 1, you add the placeholder value. If you have a value of 0 in any of the placeholder slots, you do not add the placeholder value. So in this case, you would add 128, okay, plus 32, plus 8. And you should get 168, right? Now, that being said, what would be the decimal equivalent of this? This is where I need my thinking music. All right, who's going to get there first? What is the decimal equivalent of that binary octet there? Okay, Macklin says 209. Anybody concur with that? So I'm adding up what? 128 plus 64 plus 16 plus 1. Does that add up to 209? Yes, it does. All right, very well done. That's how you translate binary to decimal or decimal to binary, okay? And it works like that all across the board every time. Okay? Now, here's another thing. If you have all zeros like this, then the value of that address is obviously 0. If you have any of these where you turn on all of the binary bits, the value of that is 255. Now, when we are assigning IP addresses into a network subsegment or a subnet, we take the 0 away because that is, again, not a real number in numeric systems. So in essence, we discard that 0. And 255 is what's called a broadcast address. For instance, if I wanted to broadcast the same message to everybody in this particular network, 192.168.0, then the message that I would, the IP address that I would send that to would be 192.168.0.255. It's called a broadcast address. The high order address in a network segment of addresses. And I would only have to send that message, one message to that address would send it to everybody in that network segment. Okay. So based on that, 0 I discard, 255 is my broadcast address. That would leave me addresses 1 through 254 that I could assign to host machines inside that network. Okay. So that's the way you have to look at these this IP version 4 addressing scheme here. Okay. Now, the router I was telling you about, it makes that routing decision based upon another very important bit of data. It's called a subnet mask. There are basically 3 classes of private networks that we deal with. There's Class A, Class B, Class C, and those constitute different ranges of IP addresses. The most common private IP address range that's used, and this goes across all size enterprises, by the way, is called a Class C, and it will only accommodate 254 host addresses because I mask out the first 3 octets as my network address. Here's the way that works. There are 3 different subnet mask views that are basically associated with these private Class A, Class B, and Class C addresses. Class A private IP addresses covers 10.0.0.0 all the way up through 10.255.255.255. Okay. That actually constitutes almost 17 million available IP addresses. The subnet mask for that is 255.255. I'm sorry, .0.0.0. Super large networks. And what this says is that these last 3 octets I can use to calculate host addresses within the network address, because I'm masking that out. Okay. Now, the Class B networks, still pretty large, 65,534 available addresses, but we mask out the first 2 portions of that IP address as the network address, leaving the last 2 octets that I can use to calculate host addresses. And what it ends up being is 256 times 256 minus 2. Because remember, I cast aside the 0 and I use the higher order address as the broadcast address. Here, same thing here. 256 times 256 times 256 minus 2 is almost 17 million available addresses for this guy. Now, the most common and often used Class C addressing scheme is this guy right here. 255.255.255.0, which leaves me only the last octet, this guy right here, that I can use to calculate addresses. And remember, I throw away the 0 and reserve the top order, the 255, as the broadcast address. So I actually can only use addresses 1 through 254 to assign to host addresses. This Class C is by far the one that's used the most in private networks. Okay. Now, here's the way that subnet mask works. Let's say I want to communicate with a target system. My IP address is, let's say, 192.168.5.23. The host address that I want to communicate with, let's say, is 192.168.5.141. Okay. Now, because that is a Class C address range, okay, well, notice this is the range here, 192.168.00 all the way up to 192.168.255.255. Okay. The subnet mask here says mask out the first 3 octets of that source and target IP address are this guy here and this guy here, and ask the question, are they identical? Well, yes, they are. So that's within the same network. Okay. Now, let's say that I wanted to communicate with my address again, 192.168.5.43. And the address that I want to communicate with is 192.168.15.15. Well, same thing. Take my subnet mask, my Class C subnet mask, overlay it over the first three octets, okay, because it's 255, 255, 2550. Are those identical? No, they are not. That's a different network, a different subnet. So then the router says, let me look at my routing tables to find where this network here actually resides. So then it makes a decision on how what it's going to do to move my message, to route my message to that network, okay, or to that individual host machine. It performs that function based upon what we call network address translation. Private to public addresses, public to private addresses. It's designed to keep private addresses private and to only utilize public address going outbound from my perimeter router. And the router gateway device makes that decision based upon what the subnet mask is. Okay. So if I'm not in the same network, I got to route it outside. If I am within the same network, it more than likely would just bump it back to whatever switch that I'm on and say, look, you do MAC to MAC, port to port addressability. Okay. Now, here is the total range of available addresses for A, B, and C private networks. The first octet in the Class A can be anywhere from 0 all the way up to 127. There's the subnet mask. Okay. And that you will start seeing this notation here quite a bit. They call it CIDR, classless inter-domain routing. Type that term up here for you right quick. CIDR notation. Okay. And this actually says the same thing, okay, as this subnet mask. It says I am using the first 8 binary bits of the IP address is the network address. Okay, and those are the 8 binary bits that are turned on there. This says I'm using the first 2 octets of the first 16 bits as the network address. This says I'm using the first 3 octets or the first 24 binary bits. So this is the same thing as this. Okay. /16, same thing as this. /8, same thing as this. Now, because we are literally beginning to run out of available addresses, we're starting to see that notation used more and more. Okay, so they're getting away from the Class A, Class B, Class C kind of limits there that are placed on the subnet mask particularly. Okay. So that and the network address translation function is typically in the router gateway appliance. If I say I want to communicate out over the public internet, it takes my private IP address, my MAC address, my date and time stamp, the communication port I'm wanting to talk out of, and it creates an instance of that data frame without exposing those private data, and then attaches that to an outbound public domain address that goes outside over the public internet and from my router. Okay. When the response or reply comes back to that message request, then that same network address translation goes in the opposite direction. It says, okay, well, this is the communication port that I'm expecting it on. That gets translated back to this IP address and eventually to the MAC address and physically delivers it to my network adapter. Okay. So, and again, that functionality is now performed by these hybrid appliances, the network router gateway composite type of appliance. And it's all based upon how the individual network engineers set up the systems and configure individual network adapters on each and every host machine inside the entire network. Okay. Now, you can configure it manually, like in this instance here. I prefer not to do that because if you want to see somebody make a mess of network addresses, turn old dyslexic Donnie loose on it. Yeah, buddy. Require that I key all this information in here. I can make a mess of that better than anybody you know. You can have it done dynamically, which is my preference, and have the DHCP server handle all that functionality. Or you can go to each individual network adapter on each individual computer, key whatever IP address you want to always be assigned to those. Okay. And you can either put, most of them have the subnet mask entry here. The later versions of it uses the prefix link, that CIDR notation. You also need to give it the IP address of your gateway appliance, which is typically the router that's closest to you. And you'll notice here the gateway and the DNS are the same IP address. That's that composite stuff I was talking about, aggregating those multiple functions into a singular network appliance. And then an alternate DNS, this actually just happens to be the DNS address of the Google DNS servers out over the public internet, 8.8.8.8. So you can either go in and manually configure all that information for each and every network adapter, or my preference is you configure all of that in the DHCP server, okay, and let it manage all of that. It does a much more efficient job of it in essence. Here's something you absolutely got to remember. This address is referred to as an APIPA address, APIPA. Automatic private IP addressing. They always, and did I mention always, begin with 169.254. 169.254. APIPA, embed that, an automatic private IP address always begins with 169.254. And here's the reason you get an APIPA address. If you log into a session, normally I was telling you guys earlier, your network adapter presents your MAC address to whatever the closest DHCP server is to you. And that's usually incorporated in the closest router box. If for some reason your host computer cannot make contact with that DHCP server and get your IP address delivered to you, Windows kicks in and will automatically assign you one of these APIPA addresses. And what do they always begin with? 169.254. So if one of your users out in the field calls you up going, I logged into the network. I can communicate with everybody in my department that, they're hooked up to the same switch, but I can't talk to HR. I can't communicate out over the public internet. Well, there's a command that I can either have them run or go and run it myself. And we'll look at it in more detail later on. It's called ipconfig, IP configuration command. It shows me what my IP configuration on my computer happens to be. If they come back and then tell me, you ask, well, what's your IP address showing? Well, it's 169.254.5.16. You know that they were not able to make contact with their DHCP server. That's the only thing that causes an APIPA address to show up on a host machine. You will get asked a question about that. Remember that 169.254. And the reason you get it is because for some reason, the DHCP server is down. The link between your switch and that server is down. Something is not allowing you to communicate with that DHCP server. Okay. The typically, and we're going to take our lunch break here in just a sec. Typically, you go into your router gateway appliance and you configure it to be the DHCP server. You can configure the range of IP addresses that you want it to manage for you for the particular systems that are using it. Its IP address will be shown here. and the subnet mask for all of that particular network subsegment. So, and you set it up to automatically assign, dynamically assign IP addresses from within this pool or this range of available addresses. When it does that automatic assignment, it automatically takes that IP address out of its pool so that it doesn't assign duplicate addresses out in the field. Okay. So that dynamic nature there is absolutely the way to go. And for the most part, you'll configure that DHCP and oftentimes the DNS server as well in the gateway router box too. Okay. All right, for all you folks that have joined us from YouTube, we're going to be signing off now. Thank you very much for joining us today. We welcome you back. We'll be broadcasting live out there on YouTube periodically throughout the week, I think. For you folks that have joined us now to audit the class, once again, thank you very much for joining us. Let me give you guys my email address right quick. If you have any If you have anything that comes to you after you've left the class, feel free to drop me an email, and I swear with my hand up, I always answer emails, always. Okay. So again, thank you guys for joining us. We're going to be taking our lunch break now, and we're going to be logging off for the YouTube broadcast today. So again, thanks everybody out there, and hope to see you all in a class real soon. Now, any questions before I go ahead and set up the timer for our lunch break here? I'm going to have set up an hour timer here. That will give us plenty of time to grab some quick lunch and to, have the latrine break and sort of clear our mind, body, and spirit. And then we'll come on back in here and figure up this, configure or finish this lesson. And we got one more lesson we're going to do this afternoon. So any questions, anyone, before I go ahead and pull the trigger on this timer here and we take our lunch break? All right. Thank you so much. I will see you guys back here in an hour. Be safe and enjoy that. Let me back that up and put it back to an hour there like I promised. All right. You guys be safe during lunch. I'll see you back here in a little while.